Okay, so I think we should start. It's already 2:05.
Okay.
Yeah,
start the presentation.
Yeah.
Okay. So good morning, good evening, and good afternoon to everybody. Manuel Gonzalez Bergas and I, Marco Lonza, welcome you to the Data Science and Machine Learning Workshop at the ICALEPCS 2021 conference. Actually, we should speak about the second workshop because we are quite successful workshop 2 years ago at the ICALEPCS in 2019 conference and in Manhattan, New York. This is a picture of that event. We had more than 100 registered people. Today we have a lot of registrations, up to more than 200, sorry. Now the online people are increasing. I don't know if we'll reach the 200, but we are on the right way. Due to COVID, of course, the picture of the workshop will be the same. It would likely seem like this. Anyway, thank you very much for all the people who registered and are participating. So we hope that with your help, your contributions, we have the same success as the previous workshop. Why Manuel and I decided to organize this workshop? Besides the growth of interest in the world for data science and machine learning, we also noticed that
I would say, as a first approach, is raise your hand.
That the number of papers regarding expertise in machine learning, artificial intelligence in general, is growing. So this the graph shows the number of papers, and also in this conference there are about 25 papers on data science and machine learning. So also in the conference there is a growing interest. The interesting thing is that we have many tracks, many sessions, which include papers regarding these topics. You can see that also the number of tracks through the past conferences is growing. This means that these disciplines can be applied to different areas of control systems. So in this conference, there are 4 sessions where you can find papers about machine learning and data science next week at the conference. So the final conclusion of the workshop in 2019 mentioned the continuous growth of data science and machine learning, but also the difficulty to apply them and to creating really usable applications. So in this workshop, we propose to you to focus on the implementation and operational aspects. There are a number of issues and question marks related to this. And here we have listed some of them that could become recurrent during the workshop. So I'm briefly summarizing them. Are data science, machine learning applications in accelerator mature ready? And then are we still in the R&D phase, or we already have stable applications to be used routinely during operations? And regarding usability, are machine learning applications easy to train and to validate? Can they be autonomous, or they still need expert people to be operated? Another questions then concern machine learning for the modelless optimization. When is machine learning competitive with respect to classical optimization algorithm? such as gradient descent, mid, power, etc. And then about reliability, is reliability another important aspect? So can we trust on black box machine learning models for critical operations? And finally, in conclusion, what are the areas of improvement in order to make machine learning applications become really usable? So these are some of the suggested starting points we would like the speakers and also the audience to take into account in their presentation and questions. Okay, thank you. And I'll leave the floor to Manuel.
Yes, so very quickly, in terms of the workshop format, as you discovered already when we contacted you some weeks ago, we are not covering tutorials this time, that we don't have enough time, and also because of the format itself of the workshop, but doesn't make much sense to have tutorials. We gave you the links to the tutorials of the previous workshop, very interesting tutorials by Alfredo and Gianluca, and there are many tutorials online also that you can find. So Gianluca, I think he's not here today, but for the curiosity, there is 2 of his students or former students that will be presented later today. So Marco? Yeah, in terms of the style of the workshop, we insist that we want to keep it as possible informal and interactive. So really try to have discussions. We are not yet in the conference, so it's very informal. Don't hesitate to ask questions, even if you think they don't make sense. The presentations themselves are going to cover successful and I think in some cases not so successful stories, what has been learned. We aim to cover practical issues and problems that were encountered. There's several people in the audience I'm presenting that are experts, and so it's an opportunity to benefit from them. And we hope that this will be a starting point for you to make the contact and then continue discussions in the conference or later by another means. So Marco. Yeah, in terms of the agenda, we are now in the introduction. Then we will move on to the overview session where we have invited the 3 top experts in the world to tell us about what they are doing in their facilities, in their labs. Then after that, we'll have a quick break. And then we will, during the break, we will try to take a group picture if we manage to do so, but at least let's try. It will be the first time I do it with Zoom, so let's see if it works. And then after that, we'll move to more specific presentation about different projects. Then in the end, we'll have a schedule sometime for discussions. There's already one person who's submitting some topic for discussion, and then some conclusion. Also, each of the presentations themselves will have time allocated for questions. So yeah, please use it for us to ask questions and trigger discussions. Yeah, Marco. Some very quick guidelines. So please keep your micro muted. I think there was already somebody who had it unmute. If you want to ask a question, you can raise the hand in the Zoom menu and we will give you the floor. We will enable your video. We'll give you the floor and then you can enable your video and unmute. If there are technical issues, if they are only affecting one person, you can contact directly. There's 2 people in the connected, Jinping and Pengxian. They are marked as staff, so they can help you solve technical issues. Unfortunately, given the time schedule and the number of people, we cannot really stop the workshop waiting for a personal problem. So we'll try to solve it in this way. If you still have any latest last minute discussion you want to trigger for the last session, you can still tell us, Marco and myself, and then we will try to include in the last part. And also something we cannot do because we are not in person, but something we appreciate a lot in New York was to be able to discuss with you after the workshop about feedback to things that you see could be improved or could be in a different way. So we will stay in the Zoom meeting after the workshop for a few minutes, but you can also contact us by email or during the conference afterwards. So Marco, and yes, this final slide is very nice picture of where, so that there are different stages for any data analytics project. So I think today we will see different stages of the people presenting, and also to stress that you should not be shy to ask, even if you are at the very early stage of your project, or if you don't even have a project and you're thinking if the techniques today can be applied, don't be shy and ask questions. And yeah, this is all. I don't know if there are any questions. Not yet. So I think we can move to the overview session, Mark.
Yeah. So then, as mentioned by Manuel, the first talk here is an overview on machine learning techniques used for accelerator physics. It will be given by Pierre Snitzer. Pierre is an experimental physicist from education, acquired experience in light optics, accelerator magnet design, and their tests and measurement next to the field parameterization. He's an associate editor of ICALEPCS transaction on applied superconductivity and lecturer at University of Mainz, where he gives courses on machine learning for accelerator physics. He worked for LHC and the FAIR projects. Now he is with Helmholtz Zentrum Berlin, where he focuses on digital twins and machine learning for improving accelerator performance for BC2 and the upcoming machines. So please, Pierre, can share your screen.
Can you see my slide?
Yeah.
Yes. Thanks, and you can hear me, I guess.
Yes.
Yes, thanks.
Yes.
Thanks to the organizers for giving the opportunity here. I will give you an overview, let's say a high-bird's view over all the different topics of machine learning that I see that will be useful for accelerators. I'll cover shortly statistical learning, only a few words on networks because I think they will be covered by other talks. And otherwise, reinforcement learning is useful for accelerators, and an outlook to explain machine learning. And I touch shortly the non-learning part, which I see of equal importance. Yeah, as we all know, machine learning has the different approaches, like supervised learning that we as physicists hand-wavingly often think quite similar to regression, or algorithms could find a structure, what you consider as unsupervised learning, where I really like this statement of Rutherford Roger, we are drowning in information and starving for knowledge, where unsupervised learning can help to find structures. Or we can learn from the environment. I think we all have heard about AlphaGo. This first implementation that could beat human beings on a Go game, which is based on reinforcement learning. I think what one never should forget when it comes down to machine learning, like Elena said at the EPAC 20, machine learning is about learning from the data, not about application of a particular intelligent technique. As a physicist, I still see that a lot of these approaches basically are, how to say, combined simple Lego blocks that you combine to complex models that have a lot of parameters and giving a lot of data. They can be very flexible what they can represent. Yeah, as physicists, what you really should learn about is random variable statistic distributions, pre or posteriori, Bayesian rules, additive models, tree networks, and in particular Bellman equation. Yeah, I wanted to show that because that had happened close to Bessie, I think in the 10th of the last century, first flight with 4 passengers on a plane. Why do I want to show you? Because like the pilot said, with a big enough engine, you can make a Bandor fly. What I want to stretch here is basically, yes, with machine learning, often what one has to find is the most appropriate algorithm for the task. But when you get started, I think it's very good that you don't worry too much if it's the most favorite one, because often it will take you somewhere, even if you waste a bit of CPUs, but you learn a lot getting your hands dirty. I want to start to remind you that there are very common examples where machine learning is already used in accelerators. And one, for example, is regularization, which you often have heard as Tikhonov regularization, an idea of the 30s of last century, or typically implemented as ridge. And what it's all about is that you have measured the orbit response that each individual steer in an accelerator will give you. And then you have this measurements of the steerers. And with the steers, you want, the measurement of the beam position monitors and the measurements you want to calculate back which steer settings gives you the ideal orbit. But the individual steers basically work with each other. And with such a regularization, you basically can find the settings with the low current settings on the steer still gives you quite a good orbit, and they're not fighting so much with each other. Why I show you that example, because you can see that it's basically these days 2 or 3 lines of code to implement this regularization part. Second example that I wanted to give you is, for example, this centralized search, where we want to identify different spots. Here's this 3-camera measurement, and we want to find the 7 spots. All that we have to do is get values about the threshold, make them equally in size, so scaling. In the end, a Cummings just finds the different spots directly. So what I wanted to show you with these 2 slides, that often the statistical learning can come handy for rather straightforward problems, and it's only a very little code that you need to implement that. Gaussian processes. I think it's always good that one still knows how they work, because as physicists, we're taught, at least if you're my age, about regression, and regression, it's typically a fit, and all you're thinking about is minimizing the distance. On the other hand, I think one is really good that when you use the Bayesian approach, and that's instead of minimal distance to the data points, you think that at each data point you have a representative of a distribution, and you want to find the line that represents the most probable outcome. And basically what a Gaussian process is that you take this idea a bit further, you have a set of probable functions, you compute the covariance between the functions, and you bring in a characteristic length, and the data points then give you the most probable function. And then you can put that further, and for example, you can then see where this thread is, you find an upper confidence bound, and then you would say, yeah, that's the most probable, for example, here, but you add a bit of noise, then you would mix up this bound, and you would find another point which could be more probable, and then you explore a bit more than the ideal part. The most interesting example that I found, no, not the most interesting, but a compelling example is what Søren Hjells and others did at DAISY for laser plasma acceleration, that they put in 3 different values. You have here the gases, the control, and other values, which would be a huge area you have to find. And what they could do is that the energy spread of the laser plasma is something like 25% if not controlled, and they got it down to something like 0.7% with something like 100 trials. And that's one of the best examples that I see in accelerator physics where you really see it apply. You can apply it quite straightforwardly. Yeah. Other example is trees. So with trees, you basically split up your area in basically your set in subsets of common value. And if you have a problem like that, a tree will easily find that and represent. But typically, our data doesn't look like that. An interesting concept is then boosting, whereas the first tree is making an approximation like that. You then take the difference from your data to this approximation, the next tree learns on that, and so on. And this boosting is working quite nicely. Random forests is the other a version of that. No, not a reversion, sorry, too early. Random forests, what you then do at each point, from your many independents or labels or features, you select a subset, and only of that you find the most with the most variance, and then you develop a tree, and you then develop a lot of trees, and you combine the results. These are pretty straightforward and very fast. And you can take that one further and make isolation forests. So that's what Elena has done, I think, at LC. I hope I don't spoil now Varena's talk, but I think that was a very nice show of such an experiment where you basically, what you do, you have the different measurements in the feature, and you see that this one is split in the beginning. We split them further. And the interesting part is with isolation forests, you don't do that only once, but similar like with random forests, you always do it on the different features, and you find that certain points are very early split apart and go ahead. And that way she could show us all this BPM data that you could identify broken BPMs, and BPMs die frequently. So that's a really nice example what you can do with such an approach. But the maths, in the end, if you look into it, is rather straightforward. I won't give you a lot on network. I think Aurelien will give you a lot. Networks, you typically have an input layer, an output layer, and in the end, you basically, as a physicist, you could say you try to fit, but the compelling argument is this hidden layer where you have a lot of hidden layers, and you have a rather simple function in here that tries to learn that layer, and you will shift the basically the okay, sorry, and you have then a simple function like, for example, ReLU in this hidden layer, where the network learns where to shift the start and how much to scale that, so the network learns from this data, how much of this data led to pass and how much to scale it off, and it goes over to the end. But that's not the only point why it's working so nicely. The reason is also because you can do a back propagation and you can do, the network itself can compute its gradient. In that manner, you can use the difference in the end and propagate it backwards, and all the weights and scales are adjusted. And that was the reason that networks have been spread so far. I want to give you here again an example, and the main reason I give you here is again to show you that it's not so much code that you need in the end to implement something like that. As a colleague of mine has done, we're trying to forecast the vertical beam size of the electron beam in BESI2, and this beam size varies. It's a differential beam size here, but we plotted. It varies depending on the setting of the insertion device and other settings, and we can see that from week to week we have a different offset. And this long-term memory learns very fast to adapt to it. It learns history, but on the other hand, it also learns when to forget about history. And you see that it works nicely in training data. It worked also on test data, but what you can see here, it didn't represent yet this peak. On the other hand, one can argue if you need to represent it or not. Main reason to show you this example is to build this model, you need only a few lines of code, and you will spend more time basically getting data in and out into the model and to train it than really to build the model itself. It will take a bit of time to find out which model is the right one. I want to spend a few words on reinforcement learning. Reinforcement learning, why is it interesting to us? Well, it's built on Markov decision processes, which basically say that the current state is enough to predict the future. For example, as a chess game, you pass by a chess game played in the park, you see the figures on the board, and you can basically tell how the game will go ahead. Well, I can't, but if you experience the chess player. So what we have an actor, which would be in standard control theory, the controller. It's applying action on a control signal. We have an environment, which is you can consider like a plan that, or the controller, or the supervised signals, and they basically give you a state, you get rewards. Basically, you win the game or not, or how well you control the beam. The interesting part is that learning that the actor learns a policy, well, how to play, for example, for the chess, how to make the next move, and very often also value function. How likely in chess you would be to win given that you made this move, or the longer term rewards for these actions. So for learning, and the interesting part is also that the reinforcement learning is able to learn the long-term outcome, not only for the next step, and furthermore to estimate the variation. And the solution is found basically, that was it's given by Bellman's equation. It's sufficient to be optimal at each step. Yeah, and if you're controlling accelerators or other big size experiments, well, control is learned playing games, interacting with accelerators. Yeah, it needs a bit of good nerves when you're operating on the beam, especially on 300 milliamps an electron beam. But of course, an electron beam is not as challenging as a proton beam, and in particular anything like an LC beam. But there it's interesting to be using something like explainable AI. I don't want to spoil outcome of Louis' talk. So Louis made these experiments at FSC2. We have a problem of harmonic orbit distortions onto the beam. Our classical orbit, fast orbit feedback basically measures, uses the orbit response matrix that was measured in the individual spheres. Then you use a singular value decomposition to invert the matrix. And then you can use the beam position monitors to derive a correction for the steers. What Louis did, he extended that one and added a reinforcement agent, which is very interesting because it outperforms in certain areas the classical algorithm. So if you're interested in that, I really would like to ask you that you come to Louis' talks on Thursday, where he will give all the details. Another fascinating example is from what what has been developed at Karlsruhe, where the control, the beam, the split up of the beam due to Coherent synchrotron radiation. Where does it come from? Well, you have an electron that's deflected in a dipole or in a magnet, will emit a light, and if the bunch is short, it will emit coherent light, and then the power goes up because of the quantum mechanics nature of this light emission. So the first one emitting will basically make the others emit in the same range. And because the power goes up, that can destabilize the bunch. You mitigate that, or you can theoretically mitigate that using the RF system to control the bunch again, so how you form the bucket. And what they showed is that with reinforcement learning, you could control the bucket very nicely. And what's in particular interesting, that they did it with dedicated hardware, and they can get it down to something like 10 microseconds. So reinforcement learning can be pretty fast. Neural networks, in particular, because they can be large and have a lot of parameters, typically the humans are seen as black boxes. And one would like then to explore how the black box behaves. And one idea is then to profit from the flexibility of the networks when you make the measurements on the machine, because accelerators, you will not get so much time to explore them. So you want to use the flexibility that the network learns how the accelerator behaves, but later on you would like to understand how the controller behaves. For example, what if you control the beam, what will happen if one of the beam position monitors breaks? And so what one would like to do is basically derive a simplified model, for example, statistical learning one, so classical approach. And basically you would like to find such a model that it represents the network, what the network learned as a black box. So you use the original data and the trained network, and you want to use that. Then if you have something like that, you can understand the network's behavior. That will not be feasible completely all the time. So what the other approaches have been developed lately is, for example, a local interpretable model agnostic explanation. What you really want to do is you identify the spot, the area of solution which interests you most, and you try to find out how the network behaves in the neighborhood, and then you try to describe that with, yeah, some not too fancy linear combination model or an additive model. Another interesting approach is the so-called sharp-Lie values, where you want to make a prediction. And basically what you can think of is you distribute cards to players in a game like Tarok or Bridge, where they would put them, depending on their cards, play together. And what you give them a different cards on the hand, which you could consider the different inputs or features. And you would then see the influence of the different each features and the outcome, so how the play of the game would end. And in that manner, for example, consider that one of the BPMs, reposition monitors, gives you faulty flaky signals. You would like to know how it would influence the control of the beam. A few words on the non-learning part, on the life cycle. Yeah, basically, the first thing to worry is how you get data. And if you're not a large scale, well, not a facility like CERN, it's always that you really should control, get hands that you have data access consistent data access over the different archives. You have to develop an algorithm. You should think then on the deployment, and as soon as it's running, also important to consider how to monitor that. Time and time stamping, I consider is an important part, so that when you learn, you have really a consistent time that the data that you use of the different features belong together. When you interact, try to minimize delays. And if you consider new installations, in particular, consider something like a storage ring. Consider that it won't be a storage ring anymore as soon as you would apply something like a reinforcement learning, because then it basically becomes a transient one, because it constantly changes the states. And I think it's a good idea then to consider in the design stage to learn from best practice from, for example, like fast RAM synchrotrons, like CERN PS, GSR 18, from the techniques applied there on data gathering and so on. When it comes to deployment, accelerators have a lifespan of 30 years or more. And I think it should be aware that the software runs a long time. I use software in the BESI2 control room, which is 25 years old. So software stack, consider technical depth. Easy one is, for example, notebooks, move to input-output controllers, perhaps, to minimize the dependency of the external packages. Consider versioning and rollback. I hope I gave you a short overview of methods and fields. I mean, much more details are coming in this conference and on this workshop. When you work together with data scientists, especially if you come to main science, let the data science experiment with the data, because it can reveal new insights. I think it's good that the main and data science work closely together, because you have an exchange of knowledge, experience, best practice. I worked a lot together with Louis, who is a mathematician by training. I saw that when we worked together, that he got more and more an experienced experimental physicist, and more and more pushing the edge how you should do experiments. I don't know how much I learned with working with him, but I think it was a common good experience. Thanks for your attention.
Thank you, Pierre. So we have 8 minutes for questions. Please ask freely. Raise your hands if there is any question. I don't know if I'm looking at all of them.
If nobody else, I have a question, Marco.
Yes.
So Pierre, you talk about this applying reinforcement learning in these closed loop examples. And I think here the question that comes always is how to guarantee that you are really not going over the safety limits of the system, or that the system is behaving in a reliable way. So how can you guarantee that?
Yeah, how to say, that's why I said you need good nerves. For us, for BESI2, the machine doesn't store too much energy. And for example, during the so-called washing weeks, or the weeks where you run with full current but without users, we conduct experiments. And I think in the beginning, you just have to get confidence. If you can't afford that, I don't see any other way out than going to something like explainable machine learning, or you have to stick with Gaussian processes where you can make forecasts on the probability. Long story short, I think at this stage, you have to make up your mind if you can afford that you, for example, lose the beam in the beginning. When we conducted the experiments, we only lost a beam in the beginning. We didn't lose any beams in the last shifts. And or you really have to revert to this explainable concept. And if that's not sufficient, you have to have a classical controller that supervises your experiment and pulls the trigger in case you're getting in the unsafe mode.
Okay, so I understand you went through this, and in the end, this is now running in production. So you managed to go to production with this algorithm.
It's not in production yet.
Okay. that is near. You went through already some steps of.
Well, this was mainly a development of Luis. I was helping him here. This was really the development of Luis. I was really
Okay.
say details. Please wait for Thursday, and Luis will give them on Thursday.
Okay.
Other questions? If not, I have a question. So I'm coming back to one of my questions in the slides. So you mentioned a number of applications, and also you know other applications that you have not explained here. But how many of them are really operational, used during routine operations, and instead how many of them are just R&D? And then what are the difficulties in implementing and using them in the real world?
Yeah, okay. Let me go 2 steps back. So I'm working on a storage drawing, on an electron storage ring, some synchrotron light sources. And one thing to say that a synchrotron light source is pretty well understood and can be pretty well controlled with classical controls. I think so, and that's that the storage rings that currently operated, you will always have to run up against the standard approaches and justify that. I see that a lot of developments are coming in the linear accelerator world. I would really say one should consider to discuss that at the end of today's workshop and not now, because there you really would see, I had looked already of our other colleagues' slides, and I see that there really the development is running, and I would propose to reconvene at the end of the workshop to this question.
Okay, thank you. There's a question by Lender.
Hi. You mentioned transients in the environment of the reinforcement learning. However, I think it's standard practice that you assume that the environment is static, right? It's like these algorithms, they only work if the environment is not changing the rules. So
yes, how to say? Yes, but you know, appetite comes with eating, and the more you go ahead, the more actions you will apply. And when you roll out the actions to the machine, you have to be sure that the action have been delivered timely, consistently, and so on. And when you do something about a development like Luis did, where you really have to be fast, and you have not only the single step, but the system also learns how it responds on the long term, by step, then it's really important to ensure that you meet the real-time targets. So and then you have to worry about delivering actions on time, that all individual devices work together, act together. And basically it also means you can reduce on the real-time side, you can reduce the variance of your system. And that's what I wanted to mention, that yes, theoretically, the whole system assumes that it's step by step. On the other hand, you have variants that it can tackle with.
Can it maybe be used also for anomaly detection? Because if you trained on an environment which was static and then the environment changed behind your back, maybe you can use this trained agent to detect something that's working incorrectly.
Could be. I don't have personal experience on that. One has to see what other people will report.
Okay. Thank you.
Other questions? If not, thanks. Let's say thank Pierre again, and we can proceed with the next speaker.
Yes, so our next speaker is Aurelie. He's from Netherlands. So I will ask her, yeah, we're seeing the slides. So Aurelie is currently the Department of Health for Machine Learning Accelerator Directory at SLAC. She started working in AI and ML for practical accelerators applications during her graduate studies with Fermilab in 2012 until 2017. In 2018, she joined SLAC as a postdoctoral researcher. She has been, many of you know her already because she's been already very much involved in the education and accelerator community with AI and ML. For example, she was at the first ICFA workshop that took place in 2018, the machine learning for particle accelerators, and she's been also involved in other schools. So Aurelie, I give you the floor.
Thank you. Can you hear me all right and see my screen?
Yes, everything is good.
Okay, great. So I'm going to try to cover a lot of the operational challenges that we deal with, specifically at Slack, and in particular for the type of control problems and modeling problems that we're trying to address. But in general, a lot of what I'm going to talk about is very applicable to lots of other types of accelerator facilities as well, in terms of the general techniques that can be brought to bear. So to just frame what we're trying to do at LCLS, and also to some degree, we have very similar kinds of control problems at Facet, which is another accelerator at Slack. We in general are trying to serve different scientific user experiments. And for those experiments, users have very different beam requirements. And there's quite a high turnover rate. So experimenters will arrive for a few days or a week. And then it's the job of all of us to set up the machine in a way that gives the users the specific beam characteristics that they need. This is a challenging problem, as many of us who are involved in accelerators know. It's a highly nonlinear problem. You have kind of imperfect information, and you're trying to control a beam in 60 position momentum phase space, in some cases with very tight tolerances. So at LCLS specifically, generally, we're spending, based on previous year's surveys, about 400 hours a year tuning. We're changing configurations a few times a day and taking 30 minutes out of that each time. And so if you actually try to put some numbers on this, this ends up being something like an equivalent to $12 million of operational budget. And it's an amount of time that you could, if you reduced it entirely, fit in 10 additional user experiments. So that's quite a compelling reason to try to improve how quickly we can tune the accelerator. It also matters when we're trying to bring up much more challenging to achieve configurations, things like attosecond pulses that will in turn enable new science that the facility can do. So it's both a practical problem about trying to maximize scientific output and also trying to really push the edge of achievable beam parameters. So if we, ideally, we would have a nice fast executing model that predicts the output of the accelerator well, and we could just offline, predict the setup that we need for a particular user experiment and then apply it to the machine. In reality, we deal with a lot of practical challenges. These are all examples from Slack. So for instance, for the FEL, our simulations, even when we try to include all of the nonlinear collective effects that are expected, don't match up with measurements that well. We have lots of fluctuations and sources of noise. So this is, for example, a laser transverse profile image that has changed day to day. There are unexplained sources of drift that can be difficult to pin down and therefore difficult to model. And then we're also, particularly with the free electron laser that we have, our output fundamentally relies on a nonlinear instability. So that also makes it challenging to model and control. So in practice, we're relying very heavily on operators for tuning. And if you start to look at what operators are doing, you quickly see that it's kind of this combination of heuristic model learning, heuristic control policy learning, local feedback, and quite a lot of complicated, rapid data analysis of time series and images on the screen. So that essentially maps onto the areas that we're trying to pursue in order to improve accelerator operation. And that involves integrating AI and ML in a variety of different ways. So I'll touch on each of these. To start with, one thing that we've found at Slack has been useful is to initially focus on this kind of intermediate range with regard to methods for trying to tune the accelerator. So on one extreme, you could go with a completely model-free approach and also not use any machine learning. These techniques are very transferable between machines. They're effective. However, they're not as fast as some ML-based approaches that we've been testing. On the other extreme, you could try to learn as much as possible about the overall system, try to characterize it as well as you can, and then use things like global feed-forward corrections, and basically go back to the kind of picture I showed earlier as much as possible, where you have some accurate system model that you then use to help experiment planning as well. So in between this, the sweet spot is trying to balance these and saying, with a limited amount of data and a limited number of interactions with the accelerator, can we learn as we go to then help guide optimization? And so Bayesian optimization was mentioned earlier, so I won't go into too much detail here, but the basic idea is that you're learning a probabilistic model that has some uncertainty estimate associated with it, which then allows you, as you sample points while you're trying to optimize some objective, to try to select the next point that has the greatest likelihood of giving you a better value than the settings that you're at the current position. And so we've used this at Slack. It's been used at many other accelerator facilities as well. One direction that we started taking this in at Slack was actually trying to use information from the simple physics models that we have to try to enhance Bayesian optimization even further. So in this case, this is a problem that's looking at adjusting quadrupole magnets to try to influence the X-ray pulse energy coming out of the FEL. And adjacent magnets have expected correlations between each other with regard to how they in tandem affect the X-ray pulse energy. So when you have a clear correlation like this, you can actually include it in the way you design the Gaussian process model that's used in Bayesian optimization. And when you do that, when you include that in the GP kernel, you can actually learn the ground truth in the correlated case more accurately with the same number of data points as compared with if you were just going to use a kernel that does not have any knowledge of those correlations. And in turn, that then allows you to converge much more quickly when you're doing Bayesian optimization. This was tested at LCLS, and we confirmed that in practice, this does work for our case. We also started taking it in directions where if one has a much higher dimensional model, is there an easy way to extract the expected correlations, then include that in Bayesian optimization? So that resulted in this work at SPEAR-3, where the idea was to take the Hessian of a model around the expected optimum and then use that essentially as the GP kernel correlations and then use that for tuning. And so this was demonstrated experimentally and in simulation. It was applied to this problem of tuning quadrupoles to minimize the vertical emittance, which is correlated with the beam loss rate. And so this is a very convenient, effective way of quickly extracting information from a physics model that can then help you in Bayesian optimization for online tuning. We've also started taking this in further directions where we're including not just a single objective, but multiple objectives in a way that allows you to online on an actual accelerator, fill out the full Pareto front that you would normally in accelerator physics you do with like massively parallel offline simulations. This is often done in design offline for accelerators. using multi-objective Bayesian optimization and enforcing things like smoothness in how you're adjusting the inputs now allows one to do this on an operational accelerator, which is useful for characterizing new systems, as well as finally trying to tune things so that you can select different parameter trade-offs. There's also this other aspect to these approaches, which was mentioned earlier, which is safe optimization. That's something that is extremely important in accelerators. And this is a nice example from PSI where they used Bayesian optimization that included safety constraints to try to avoid tuning in a way that would lead to intermittent drops in FEL pulse energy. So you can see here by including safety constraints in a Bayesian way while doing Bayesian optimization, they were able to tune while avoiding dropouts. So this is important if you're trying to tune while delivering to users, for example. So to go now over to kind of the more global approach, we've been trying to basically speed up and make more accurate our simulations for LCLS and FACET2. So this was one of the earlier examples that we did for LCLS. So we simulated the main accelerator, including all of the nonlinear collective effects that we expect to see. We adjusted these input parameters fairly wildly, I would say, across almost the entire operating range of the machine, and then trained a model to predict the beam phase space at the entrance of the undulator. And so what this then gives you is a representation of the machine model, which you used to have to run on a high performance computing system. It puts it in a form where you can now use it on your laptop, and we could run it in the control room. You can also start to include things like the actual laser profile as an input, which, as I mentioned earlier, different changes in the laser input, that's a major source of both noise and machine drift for us at LCLS. So a lot of folks in the accelerator community are starting to do things like this. And this is kind of a nice approach for encapsulating all of that kind of information. In these cases, as was mentioned earlier, a huge problem is actually making sure that these models are robust in the face of drift, as well as distribution shifts due to just putting the accelerator in a different operating mode. And so one thing that we've been trying to look at very carefully is performance of these models in examples that are outside of the distribution of the training data set. And I'll talk a little bit more about that later. We're also then trying to use these models to find sources of systematic error between simulations and measurements. This is an example for some emittance measurements. You can see that the neural network that's been trained on simulation data, as well as the simulation data itself, is offset from the measured data, but it gets kind of the qualitative shape mostly correct. And so you can actually use the neural net to iterate very quickly over potential sources of systematic error and find things like, what could be calibration offsets in things like a solenoid to account for this kind of offset. So that this type of thing is another area that we're trying to develop further and basically convince ourselves that we can apply it in a robust way. Once you have a model, how might you use it in online tuning of the kind that I mentioned earlier? One way is to just use it simply to try to counteract drift in upstream parameters. So this was an example from the UCLA Pegasus facility where they were trying to run round flat beam transforms, but there's a lot of drift in the upstream inputs, which resulted in you needing to change the quadrupole values that are used to optimize for this flat beam. And so we trained a neural network model on archive data. And then at every time step, we read readings for the other upstream drifting inputs, and then online ran a multi-objective genetic algorithm to optimize the flat beam quad settings to then get a good trade-off between the X and Y beam sizes, and then apply that to the machine and see how close it got. And in this case, this worked reasonably well. Of course, this was for a limited run. This is not used in operation by any means. And the thing here that was also useful in convincing ourselves about some reasonable approaches to use these things in tandem was using the initial guess from the neural net, in this case, actually months later, after the initial training, to get to a roughly good initial set of conditions, and then fine tune with other methods that are more focused on local adjustment of parameters to then get a good result. So this starting with the global model and then following it up with fine tuning with these other methods dramatically increases the rate at which dramatically increases the convergence speed altogether. So this is a nice example of the tandem approach. This is just another example of essentially the same thing, but instead of optimizing around a forward model, you can also train an inverse model. So in this case, looking at a target being phase space at LCLS, you can predict what the upstream, some of the upstream settings that speak to the longitudinal phase space should be, and then fine tune with a local optimizer. And we found that the combined approach was much more effective than just using a feedback or model-free optimization alone. I think so the other kind of offshoot of this is that we also in some cases don't necessarily need a complete machine model, but we just need some way of getting a prediction for what some particular diagnostic output might show at a given point in time. This can be the case if you have a destructive diagnostic that can't be running during user delivery. It could also be the case that maybe you want to move a diagnostic station around in the machine, and so it's only at one location at a time, but you might want an estimate of what it showed, what it would show if you had it in that location still. And so we've at this point looked at a variety of different ways of doing this. So one way is to, based on available signals, tune a simple physics model. Another way is to use machine learning. So this is an example from a few years ago at LCLS. And then you can also this used a combination of simple methods. And then you can also use kind of more complicated signals to try to predict the output. So in this case, we were using upstream settings and some scalars to predict the longitudinal phase space. And then this case on the bottom right was an extension where instead of using scalar inputs, a different type of diagnostic was used to then predict the longitudinal phase space, basically spectral information using to then give an estimate of the longitudinal phase space. All of these methods have this issue of drift. So in accelerators, we're obviously not dealing with stationary systems. They're changing all the time due to hidden parameters, as well as component replacements. Some devices change their response over time. Things like the cathode quantum efficiency go down. And so if you have trained a model, this is showing model predictions on test data for a region of, for a series of days where it had been exposed to training data. And then later on, we just did not update the model at all, had its output predictions given, and then compared it with what we were seeing. And you can see the model predictions themselves degrade But in addition to that, in this case, we were trying to use methods to give us an estimate of the uncertainty in the predictions. In this case, just a simple ensemble. And you can see that actually the uncertainty band doesn't actually cover the true error. The relative magnitude is larger than where the model was more accurate. So it gives a relative indicator of performance, but not a quantitative one. And so this is a challenge, both in terms of keeping models updated and actually knowing when model predictions are no longer accurate. And so we've been putting a bit of effort into trying to assess robustness of different uncertainty quantification methods combined with machine learning. So this includes things like quantile regression, ensembles, like the example I just showed, combining neural nets and Gaussian processes in various ways, and then also using Bayesian neural nets. And so we've been looking at this for a variety of cases, essentially trying to see where each of them fail, which ones have better calibrated errors out of the box, this kind of thing. This is all, I would say, early days, but it's something that we know that we need. Okay, so I went through a lot of individual examples that are in their own separate boxes of AI ML applications. If we want to put it all together, then we start to need to look at things on the system level. So we're starting to do this in a limited way. The approach that we're taking right now is to train surrogate models from simulations offline on high performance computing clusters. Then take those fast executing representations, optimize them on the fly around different working points, get expected kernel correlations, then use those in Bayesian optimization for tuning. And along with that, we're also then trying to run, take data from the machine and continuously run more simulations so that as the machine goes into new regions of parameter space, we're capturing that, as well as then trying to calibrate those models as the machine changes and as we enter new regions of parameter space, and then replace those in this online tuning loop. So one of the pieces of this is simply that offline part, and we have put a lot of work into trying to make that as streamlined as possible. So we have a set of tools, Lume and XOpt, that we actually developed in part through this process of trying to address these operational challenges. And what this allows you to do is, in a very simulation agnostic way, run efficient optimizers around simulations, and then generate data sets from that are very easy to interact with. So for example, this is for the LCLS injector, and we had run a multi-objective genetic algorithm using XOpt on our impact simulation. And then from that, you end up with a sort of summary file that has all of the labeled inputs for each iteration. It has extra metadata about the simulation that was run. It has all of the constraints and objectives, et cetera, that were used in that particular optimization run. And then it also saves more detailed H5 files with beam distributions. And because we're using this OpenPMD beam physics extension, which is a standard, OpenPMD is a standard developed by Berkeley and others as a standard way of saving particle distributions. And so now with this, for any of these runs in the simulation data set, we can just use OpenPMD beam physics, select a screen that we want to look at, and then very simply, plot different parts of phase space, et cetera. So it makes it very easy to also process large data sets. So then once we've made all that data, we trained a surrogate model for the LCLS injector, both predicting things like face space and scalars. And then we've been using that offline to prototype optimization algorithms that we then want to use on the machine. And then also integrating the models into online use in the control room. So this is an example where an EPIC server is rung up, and then it launches an interactive GUI that someone can manually interact with. And it also streams EPIC's PVs back to the control system, and then has a display that can be viewed in the control room live based on what the upstream readings of the inputs are. And so this is all also using Lume model and Lume EPICS, which you can find out more about on this website. One of our software engineers put together a nice demo of this early demo of this interface on Binder that you can just run in a browser. So I encourage you to check that out. And we're iterating on this. This what I'm showing right now is a very much earlier prototype, and right now we're starting to refine this and actually fully integrate it into our workflow. We're also running Impact-T online now using the same set of tools. And we're working on the database design as for saving all of this data so that we have basically parallel archives of machine measurements and physics simulations. The last piece of that puzzle is then using all of that for optimization. And so we've started doing this for the LCLS injector as well. And what we found with this was that even though we had some discrepancies between the predictions from the simulation model and measured data, the correlations that are displayed in the model are actually still useful in Bayesian optimization when using this approach where you get the kernel correlations from the surrogate model. And so in this case, we were able to converge much more quickly than with the standard kernel. And in this case, the emittance measurement itself is actually a big challenge. We're using quadruple scans. And so there's a robustness challenge. And then each measurement is also slow. It takes 3 to 4 minutes for each point. And so this is also still a very slow optimization process. And so the next kind of question is, rather than using the surrogate model that was just trained on simulation, can we bootstrap the GP model that's used in tuning with points from a previous run? So you can imagine this might help if the machine is in a somewhat similar state, or it might hurt convergence if the machine is in a very different state. And so the robustness of doing this is something that we're examining now as we try to transition this into regular operations. What we found in some initial tests was that we were able to converge better than the baseline solution in 2 iterations. So that is a big improvement for the standard injector tuning that we do at LCLS. So the direction that we're starting to head in with those example prototypes for the LCLS injector is more fully integrating this into the overall control system and workflow. So we already have pieces of a lot of this. Some of them we've glued together, many we have not, and we certainly have not done it at scale. So addressing those challenges is something that we're trying to do now. We do have high performance computing clusters on site that in principle can help in this workflow. So basically that can be a place where we're running these high fidelity physics simulations, doing adaptation of the global models, even saving models at different working points, and then using those updated models in online optimization using the approaches that I mentioned previously. And the interesting thing about this too is that at SLAC, because we've got LCLS and Facet2 co-located, and they both use EPICS, they both can share this high performance computing infrastructure, and they have very high level similar layouts, even though they're operating at very different machine parameters. We can in principle use a lot of these same workflows and even potentially some of the same learned ML representations for both. So that's an area that we're very interested in exploring. To get to some of the major practical challenges, I'm going to borrow some slides from the UsePass class that we taught recently. So, and I'm running out of time, so I won't belabor this, but uncertainties in time varying behavior are a huge challenge. As I showed, even getting accurate uncertainty estimates to know when you need to retrain a model is a huge challenge. And this is really essential if we want to use these techniques reliably in accelerators, especially in the case of control, but also in the virtual diagnostic case, for instance, one of the applications is providing users with a signal that they wouldn't normally have to help with their data analysis. So in that case, you also really want to know how much they can trust that signal. Another major practical issue that we certainly encounter at LCLS and FASA as well is just the sheer challenge of dealing with the data. So at LCLS, we have hundreds of potential parameters that we can use that are measured in the archive, and it's not easy to narrow down exactly which one should be used. This is where some ML may be able to play a role with things like automatic feature selection and anomaly detection to cut out operating modes that might not be good to learn from if there was something going wrong with the accelerator, for example. And then there's also challenges with disparate sources of data. So sometimes there's really important information that's in the E-log, but you would never know it from the data itself. So these are all major challenges. Another
Aurelie, I think we're running out of time. Yeah.
Okay.
Yeah.
Okay. I'll just end there. Yeah, I'll upload my talk so people can take a look at these last summary slides. But yes, it's a combination of major practical challenges and AI ML challenges, and we need both to get to this vision of a self-driving accelerator.
Many thanks, Aurelie, for the very impressive presentation. A lot of very, very interesting work. I think it's very impressive. So are there any questions to Aurelie? No, the audience is very quiet today. So I have maybe one, Aurelie. So you mentioned there you basically have 3 categories of approaches to deal with problems, going from more classical and simpler ones, and we went to the more advanced, where you need to really know the system you're working on. And how do you decide which one to use? Is it something you can see from the beginning, or you have to experiment and then see what is the outcome of that? Yeah, so a lot of it is based on how much data availability there is, and then how stable, so to speak, the system is expected to be. So for example, in cases where we're exploring new regions of parameter space, we'll tend to be using things like Bayesian optimization, even without any, expectations from a physics model with regard to correlations, because those approaches are in general very sample efficient with regard to getting good uncertainty estimates and a reasonable representation of what's going on locally with very, very few calls to the machine. It's also useful in cases where there's a lot of noise or a lot of drift, like a case where you would not expect a learned global model to be very stable over time.
In cases where we do have a lot of data, like a standard operating mode that has been run many times over the previous years, or parts of the accelerator that we don't expect to drift very much, in those cases, we can start to rely more on things like a neural network-based surrogate model of the system over a really wide range of input parameter space. And so it's really, this mix. If you are exploring a new region of parameter space efficiently with something like Bayesian optimization, you then can use that data to help inform later on when you're trying to train a global neural network surrogate model. So it's that's in general how we've been approaching that. How much data and what the system characteristics are.
Good, because you presented like a very, this then solution, but I guess it took time to arrive to that. So it was not that.
Yeah.
I think Marco has a question, I think.
Yes, congratulations for the huge and excellent amount of work you are doing, really. And how many people are you in your group working on that? And what is their background? So physics, computer science, controls?
Yeah, so it's been, the size of the group has been in flux over the years. In 2018, there were maybe 4 or 5 of us total, I think, really getting started with trying to apply these different approaches to LCLS as well as FACET2. Now it's quite a bit bigger and has been helped along a lot by things like SLAC's overall investment in scientific computing infrastructure, as well as the machine learning initiative at SLAC, which ties together people in different domain sciences doing machine learning. Now we have maybe 10 or 12 people, I would say, total, looking at like mainly accelerator problems. And this really runs the gamut of experience and expertise. So we have software engineers who have experience with things like EPICS, as well as high performance computing. We have had 2 mainly that we've been working with. We have machine physics experts who are also very well versed in simulations for accelerators. And then we have several postdocs who've worked on these things over the years that have more of an accelerator physics background. And then we also have people who are much more closely tied to operations, heavily involved as well, advising about which problems actually are most important to be solved, and helping to define strategy in terms of how to integrate these into the machine effectively. So it's a real mix, and it's a large undertaking.
So these people are involved full time in this.
Yeah. So most of the people who are working on AI and ML directly are either full-time or like 50-50 regular accelerator physics and machine learning. For operations support, it's a much smaller percentage of people's time, like 10%. And then for software engineers, now we have a full-time engineer working just on this. Previously, it was, again, someone splitting their time 50-50 between other software engineering work that was needed and building out these tools for machine learning.
Thank you.
Any more questions to Aurelie? I think people are maybe still processing all the very nice work you presented. I think, yeah, it would be nice to have the slides to refer to them. Okay, so if we move on then, and there are no questions, no. Then we can move on to the next presentation. It's Verena Kain coming from CERN. So Verena is currently the head of the section in charge of the superphoton synchrotron operations. For those who don't know, the SPS is the second largest accelerator at CERN. And it's a very complex accelerator that has to serve many users, not only the LHC, but also fixed target experiments and others. So Verena doesn't have an easy life, we can say. So Verena started an initiative some years ago to informally change everything about ML and data science problems in general. And this has been proven very useful to get a community around the topic. And today is going to present us several use cases that are being worked on at SAP. So Verena, I give you the floor. You can share the screen.
Okay, let me share my screen. Do you see my slides full screen?
Yeah, perfect. And we hear you very well.
Very good. Now, and I say thanks already to Aurélie because she gave a very good summary of the motivation actually why we're looking at this, and I'm a little bit short on this, and I mainly focus on various examples concerning machine learning and also optimization algorithms for CERN accelerators. And the examples are mainly from the CERN ATS Machine Learning Community Forum. So Manuel already mentioned it. So we put this together as an informal meeting place for all these various activities. And as Manuel also said, I think this was really key to get this this movement really started. And I think you will see that is really made a lot of progress in the last two to 3 years. So motivation. Now, as I said, I thanks a lot again to Aurélie for doing this in a much more detailed manner. Let me just move one of this. So we have to, for various reasons, have more automation and better modeling for increased flexibility, reproducibility, availability of our machines, and in this way, overall better accelerator performance. I think everybody is aware of that. And this automation and better modeling, this was not necessarily so easy in the past, but now we have the algorithms. Specifically at CERN, we have this classical approach where we have rather well-modeled accelerators with these models actually even online available in the control room. Now this proved extremely powerful for specifically machines like the LHC with thousands of parameters, tunable parameters if you want, but it does not solve all problems. And also the LHC actually can use this only with a very high price. It has to essentially extremely limit its flexibility. It's essentially, if you want, doing the same thing over and over again to profit from these models as they are and to stay reproducible. Now, not all machines can run like this. So there are the multi-cycling smaller machines, for example, the lower energy machines, and there are problems like hysteresis, many aspects, drifts, and so on and so forth, that don't fit so very well into our closed form sort of analytical solutions that we can then use in the control room. Or sometimes you could actually simulate for that, but then it's then in the control room online, too time consuming. But now with these new algorithms, with machine learning and actually also other advanced algorithms, if you want, we can complement the classical modeling, and I think this is the way to go. So the types of algorithms and tasks that we've been looking in the last couple of years are, of course, numerical optimizers and optimal control, and then machine learning proper for regression, computer vision, anomaly detection, trending and forecasting, and also reinforcement learning. Now, all these examples that you will see here are from the Machine Learning Community Forum. However, not even close to everything that was discussed there. So I start with numerical optimization because I think this is one of the cornerstones of any of automation that we put in place and that will come. And this is already something that has become a standard and has been there really already. I call it now the pre-machine learning community forum era. It was used for aligning, for example, the electrostatic septum, sorting out layer injection, and many other aspects. Usually, this is done in the case where there is no model available, so you use derivative-free algorithms that do not have to be model aware. And depending a little bit on the nature of the problem, there are various algorithms that have been made available in the control room. And you can see here the GUIs that are used in the control room. Some of them still, like this one here, that only offers Nelomid simplex optimization, or another version which was already at this stage in 2018 much more generic. I think the big breakthrough the next step, if you want, came through when we went for the generic optimization framework and adopted the reinforcement learning approach also for numerical optimization. So we have a Python interface at CERN and can use therefore all the packages that are available open source out there. And what we did is that we split the optimization problem from the algorithm. We used for the optimization problem or followed the principles of what OpenAI provided for reinforcement learning with the OpenAI gyms. So we created those environments for all our optimization problems that become easy plugins, if you want, to our generic optimization framework. Currently, we have only single objective problems in that case, but the whole framework is easily extendable to anything else. So we can easily plug in any new algorithm and easily plug in any new environment. And we also provided library support, if you want, but also a control room GUI that looks like this. And it's fully integrated with all the CERN settings management, everything that is around there. And it is also allowing for optimizing functions of time that are used in the cycling machines, for example, but also in the LHC. You can see an example. This is the optimization of the Lear electron cooler bump, where you can also, the users put all their custom rendering, if you want, or custom plots in as part of their environment definition, which is then a package. Now, this has been used really for many things and is being used for many things. I will not go through all the various examples here, and it's really a much longer list than this, and really all across the various machines that we have at CERN. Now, the first machine learning proper example I'll come to is regression. Obviously, this is rather interesting for us, for physicists and for people working with data. Now, they are the ideal universal function approximators. I don't think that I have to introduce any of this. There is, of course, the issue of generalization. Oli was talking about this already. Not only necessarily that actually the issue of hidden parameters, but also very much that if you have actually data then afterwards that this was not part of your training data distribution. That I think this is a really big issue, but also all the developments towards physics informed neural nets I think might actually play a big role and help with this. But so we're using this for many things and also for fitting dynamics and models, and we build surrogate models. And I'll show you a few examples for those now. Now, this is the example of a surrogate model for the beam losses versus the crystal position and angle at DSPS. So this concerns the process of slow extraction, where you put DSPS on purpose on resonance. So you have essentially a controlled instability of the beam in the horizontal plane, and you shave this beam off at an electrostatic septum and extract this beam then towards various fixed target experiments. Now, this is intrinsically lossy, and loss is a very, very big issue for any further development of these fixed target experiments. Or in having a bigger user community. So loss reduction was was of big importance, and one of the means is using crystals. Now the crystals need to be set up. They need to actually shadow the so-called electrostatic septum so have to have the right position and the right angle to have the wanted loss reduction. And you can see here this loss as a function of crystal angular position is a rather complicated function. Now, if you want to find the right sort of controller to be able to set this up quickly in the control room, you can actually simulate this, but this takes a minute for just one iteration. The people built a surrogate model on top of the simulation, and now they can train various different controllers very fast, and this actually enabled them to use this crystal in operation. Another example for this is, and concerns also actually the electrostatic septum and the slow extraction in the SPS. This is a surrogate model of the loss versus the electrostatic septum anode positions in girders. So there are 9 degrees of freedom for setting up the various anodes of the electrostatic septum. They all have to be correct to have minimum loss. It takes quite a significant amount of time if you want to set this up by hand manually. What was done here is to build a surrogate model on top of the data that was logged during the manual scans in the past to then have a surrogate model that can be used to study various automatic alignment algorithms. And you can see this here. So here's the comparison of a numerical optimizer, so power method here, that was used in 2018 and then brought down this alignment time already from 8 hours originally to 45 minutes. Now on using the surrogate model, other algorithms were then studied, for example, Kobila, that is already using a model actually in the back and then uses a linear interpolation or linear approximation to predict the next points if you want. And now this would have drastically reduced the setting up time and was a good candidate for 2021. What we in the end used was not Kobila, but BobbyQA that uses a quadratic approximation over the objective function, and this reduced the setting up time to about 10 minutes in comparison to 8 hours originally when this was done manually, and took about 30 iterations for 9 degrees of freedom. Another type of surrogate model, was used then on top of simulations. And here the problem was to train a reinforcement learning agent to optimally control the electron cooling at LEA. The simulation is done with RF track and is rather lengthy. Now, if you want to, first of all, train your agent and actually also tune the hyperparameters, this was way too time consuming and was essentially undoable. But then you can actually train a surrogate model on top of the simulation, and then this can actually be done and was done, and we now actually will be trained one of those days now on the machine. Another actually important and very useful way of using surrogate models is that one can actually do surrogate models on top of the dynamics. One can actually learn the dynamics of a certain process and then use this learned dynamics together with model predictive control. So we tried this also here with ILQR on top of the dynamics model that was learned using a neural net for trajectory steering. And you can see that the ILQR then corrects this trajectory to an RMS value that is specified with a certain threshold here in 1 to 3 steps here maximum with the model that was available after, I think, 200 iterations. Computer vision. There are also many examples concerning this. Let's start with variational autoencoders for radiation hard optical fiber imaging. Now here the story is that we have these screens that we use to image the beam or at various locations. And these need, however, very often radiation hard cameras, depending a little bit on the locations, and they're expensive, and many of them are also becoming obsolete now. Another idea is to take that light that you have from those screens, bring it away, and have the radiations and have the cameras at locations where there is a lot less radiation. Then the challenge is, of course, that you have to interpret this light that is coming out of the fibers. You can train for that, and this is what is being done here. This is what the fiber would output if you want. This is what the original light should have been or is at the screen, and after training, this is what you predict, for example. So this technique is also rather promising and is being further investigated. I will not say too much about this because I've seen in the program that Leander will talk about this later on. This is about an application at the LHC now. It's about interpreting the tune signal, so the working point in the LHC. He came up with a method to have a method that is essentially robust against the 50 Hertz noise that we also seen in our tunes spectra, and it's much less sensitive to these 50 Hertz lines than our classical approach. And this would have a very, very important implication because the tune signal input is input to the tune feedback system, and this needs, of course, a stable information. But he will talk about this much more than afterwards. Other, I think, much more classical applications of computer vision is here anomaly detection here for the dump kicker failures in the SBS and the LHC. That's working also very well, and this is actually being used online in our what we call post-mortem analysis of our beam dump systems. And here this is combining essentially computer vision with controlling. The idea here was to build a surrogate model from BTV images in awake. The challenge here was to optimize the spot size in front of the plasma cell. So WAKE is a plasma wake field acceleration test facility. So here you have these kind of spot sizes that you have depending on the settings of the wake facility or of the electron source, if you want. They trained in autoencoder, but actually extended this autoencoder with including the information essentially on the various settings of the machine. Trained the latent space that was then also again input for a model of the control configuration as a function of the latent space, or the control configuration as a function of the other way around, so the latent space as a function of the control configuration. And in this way, they essentially could also have at the same time an inverse model, and used also then the latent space as an input to reinforcement learning to HN to optimize the spot size. And another example here is LHC bunch by bunch. Sorry, I have another window here that is in my way. LHC bunch by bunch parameters from tomography using machine learning at LHC injection. So again, an autoencoder, but a supervised autoencoder this time, where they are learning the longitudinal beam parameters at injection from the longitudinal profiles. And they can do this if they use actually machine learning. If they use this autoencoder, they can do really tomography, so reconstruct the phase space and the longitudinal parameters and injection. They can do this bunch by bunch for all bunches. Online or with classical methods, it's only possible with a single bunch because it's way too time consuming to use classical tomography. We also have examples for training and forecasting. Okay, so I think many of you have heard about this. There are all these network architectures that take the past into account to predict the near future or even further future. So there are various networks, LSTMs, NARCs, etc., etc. Now, what we have tried here is to use physics-informed LSTMs. So you can see here the architecture. So it's essentially a combination of various LSTMs, if you want, to predict the main SPS protocol field depending on the history. So it essentially predict the hysteresis. And this was the only architecture so far that could actually predict the field with a good enough prediction to do actually feed-forward correction. So this works rather well. Another example using LSTMs is the prediction of the temperature evolution of the SPS injection kicker that heats up with LHC type beam in the machine as a function of intensity. Now, this information is important to optimize what is called the scrubbing run. So the preparation essentially of the SPS for being able to run with 25 nanosecond beams. So 25 nanosecond beams cause the electron cloud effect. And the mitigation for having too much electron cloud is to essentially scrub the vacuum chambers, to bombard the vacuum chambers with even more electron cloud. The only problem with the scrubbing runs is that you'll have to have 25 nanosecond beam circulating for a very long time. And this causes beam-induced heating, specifically in this injection kicker. And if it goes above a certain temperature, you can't run anymore. So you need to be able to deal with this, and you need to tightly control this to have a minimum scrubbing time. And you can predict this now with LSTMs. You can predict with the given intensities that were circulating when it is best to actually have a switch into cool down mode and when to carry on again with scrubbing. And the final example concerns reinforcement learning. So it has been talked about, it has been introduced also, so I will not go into many details here either. So we've also seen that the importance of automated tuning and optimization, and that's sort of the how much time one gains automating some of these aspects, specifically if they are higher dimensional. Issue with numerical optimizers is that they need to explore each time again. So some of them are very good. They use models and they become very fast, probabilistic models or deterministic models. This helps, but nevertheless, they need an exploration phase each time. There are, however, these algorithms, we've talked about them, reinforcement learning, that because they learn the underlying dynamics implicitly or explicitly, that actually can do without this exploration phase and know how to act given the state information. And okay, the learning, I think this was introduced as well. The learning is done to this training of these agents. So these algorithms need to be trained first. This needs to be done through reward. Okay, so I will not go into further detail about this. I think this is rather clear. But I'll just show you a few examples. So this is rather old now, but this was nevertheless one of the first ones that we did online on the machine with real beam and for a problem that is actually solved classically, but we wanted to see what it is, where we can get with reinforcement learning agents and whether they actually work as well as the classical models. And they do. So you can see here the training of a reinforcement learning agent. So this was Q-learning with the very sample efficient NAF algorithm on trajectory steering at awake in the horizontal plane, 11 degrees of freedom. And you can see that at the beginning, this agent takes many iterations, up to 50, to correct the trajectory along the line to an RMS below, this was here 2 millimeters. That was the, sort of the target threshold. And from these initial thresholds, initial RMS in green here. And then after a while, it learns how to correct this line within 1 or 2 iterations each time from any of these initial trajectories. We tried this then also at LINAC 4. Now LINAC 4 was already more interesting because LINAC 4, or the Linux in general, they do not have these models that are mentioned at the very beginning, a la LHC, and they did not at this stage have any automatic trajectory correction algorithms. So this could have been a solution for them. It was trained in about 250 iterations. This is 16 degrees of freedom and also worked very well. And it then corrects each time to an RMS that is below 1 millimeter. Now, since then, we had many more examples for awake auto matching. I mentioned this earlier, LHC tune control. I think Leander will come back to this, control of the PSRF manipulations, and many more. Another thing, interesting technique one has to keep in mind, I think, is okay, one can go model-based, then one has another very good side product as well. One actually has the explicit model dynamics as well, then after the training. But what one could do also, if one has very good simulations, is that one trains on simulation and then uses the controller on the machine afterwards. We've tried that as well, and of course that works very well. And we've also started playing with very new techniques. We've also tried to look into quantum reinforcement learning. This is using quantum annealers with quantum Boltzmann machines, and again, because it's rather straightforward and easily always to compare and to understand, we used again trajectory steering, this time not in awake, but actually towards one of the fixed target experiments in the beam transport there. And yeah, so we compared this quantum Boltzmann machines on these quantum annealers with the classical DQN. So we were discrete at the beginning, and then the simulating quantum annealing, and then finally the real quantum annealing on the D-wave system. And okay, so quantum computers win in terms of number of iterations that are needed. So that's maybe as expected. So another really important aspect for us to actually do all this and to go further is the infrastructure and framework. So I mentioned already the generic optimization framework, but we have to go many steps further. I think some of the things are rather well set up already at CERN with embracing Python, for example, and various other aspects. But what we needed still was to be able to store and load neural nets in the CERN control system. So this has also been provided in collaboration with one of our control groups. So we can essentially, using these packages here, we can actually just call our neural nets like a mathematical function from within our codes and within our applications. And another aspect is also always hardware, GPUs, and also, as you can as you could see on one of the last slides, maybe even quantum computers. So in order to not to not having to buy all this hardware and having lots of idle time or having batch systems, etc., etc. What we participated with, and what we tried, and I think that was also actually working rather well, is that we participated in a cloud pilot project with Cloud Bank using the Google's and Amazon services. And this actually gave us then the access to, of course, GPUs, but also TPUs, and also namely the quantum computers. I think, and this was actually also a very, very good experience. And this brings me already to my last slide. Many of our accelerator problems that were intractable or needed lots of resources to solve are straightforward to solve with machine learning and other advanced algorithms. I think there is, at this workshop, I don't even have to mention this anymore. I think all this world, all these aspects just need to become part of our toolkit nowadays. I think I also showed you a successful demonstration in a number of examples. Now it requires some expertise and embracing new technologies. And in our case, at least for us, this machine learning community forum, which used to be called at the very beginning Machine Learning Coffee, helped to establish sufficient expertise in many of these domains, and actually also helped to establish frameworks and infrastructure. I think, and also Aurelie was mentioning this, the next step is really to go and establish a self-driving accelerator project. Not necessarily to make sure that we have self-driving accelerators, which I think would be nice also, but much more, if we have this type of project, this would give the next push for really sorting out various details and help pushing the entire field even further forward. Now, I don't think this is only machine learning and only numerical optimization and all these aspects, but I think it's a kind of a change of mindset also using our classical approaches. That's it. Thank you.
Many thanks, Verena, for the very impressive wide range of applications you've shown. It's already a challenge, I think, to follow one of them, but so for you, has to follow, maybe not in detail, but to give an overview of all of them is really, really challenging. So thanks a lot for the nice overview. And if there are any questions to Verena?
I have the question. Piotr Gorer from S2 Innovation. Just I was looking on your BPM, how it's called. This example you showed a few slides before when you did the reinforcement learning to the reinforcement learning. Do you also try to use it as for kind of predictive maintenance? Because I suppose that if you have the neural network, if you have one layer for BPMs, you will have like response matrix or inverse response matrix, and you can easily track the changes of this matrix if it's assuming it behaves like we expect. Have you tried to use this for these purposes, or thought about this?
No, so this is not, no, this is really kind of, if you want, would be a replacement of one of the classical correction algorithms, classical controllers, if you want. But there is, of course, a lot of predictive maintenance ongoing as well, using machine learning. So I didn't actually go into any of this, but this is a big topic, as you can imagine. But okay, yeah, I had to do a certain selection, but no, not this reinforcement learning agent.
Okay, thank you.
Outcome.
Maybe if I can complement, coming from the BIM instrumentation group, this is something that is somehow in our to-do list. We really need to work on that. So find the time to do the predictive maintenance for the BPMs.
Okay.
Okay, then we have a question from Anthony.
Hello, Verena. Thank you very much for interesting talk. I have a question related to the interpretation of the beam dump pattern. So here, the goal is to reconstruct the beam pattern. So it's like identity mapping, or what's the objective of this?
So okay, now our beam dump systems, actually in both machines, there are two aspects to it. The one aspect is, of course, to actually have the beam on the beam dump block. And the other aspect is to have the beam dump not just all in one spot, but actually to dilute it. So with so-called dilution kickers, draw this pattern on the beam dump block, which you can also actually see on these PTVs that we have just in front of the beam dump. Now, there are several kicker systems involved that all have to fire synchronously, etc., and they all have this like kicker systems, the switches, yeah. And if some of them, there is also some redundancy in there, but if some of them don't fire the shape or don't fire at the right moment, the shape that you have, these spirals there, for example, will change. And so what they did, they trained essentially variation autoencoders for anomaly detection that will tell how many of the kickers are good and how many of the kickers are bad, if you want, depending on the shape that you see on this PTV images.
Okay, but the classification also, is on the quality of the output, let's say. So like you are measuring your quality or the anomaliness on your predicted, let's say you have certain pattern, and then you feed your network with the pattern, and then you measure the output, and then you say, okay, so it differentiates, so too different from what I get, and then you consider it as a failure, or?
Now I can't remember now all the details, but we could have a look at it. But as far as I remember, is that we actually took the latent space, and from the latent space, they did the classification.
Okay, yeah, that makes sense, I think. Thank you.
Welcome.
Any more questions to Verena? Anthony, you still have your hand raised. I guess it's because of the previous question. Okay, yeah. No more questions. So maybe we can thank again all the speakers of the overview session. Thanks to you three. And we can try to get the group picture. So if you could all enable your video, then we can try to do a picture. In fact, we'll have to be 3 pictures because we are doesn't fit in one. Okay, I see the pictures coming. Smile, bit, cheese. Okay. Smile, cheese. Okay. So I think we are done for the picture. It was not very painful, I hope. And then I think we can convene. Marco, what do you think? When do we go back in 10 minutes? 10 past 4. I think I've lost my Marco.
Sorry, mic was off. Yes, I agree. Okay.
So it's already, yeah, maybe let's do it in 10 minutes, yeah. But maybe 15 past 4 for Geneva time. So 13 minutes from now. We're a bit late, a couple of minutes late with the agenda. Okay, see you in a while. Hello?
Hello? What do you think? We can start?
Yes, I think we can
1
resume.
minute. Yeah.
We wait a bit because there is a bit less people than before. Let's wait until 16.
Yeah. 127, I counted.
We'll have to have statistics afterwards about peak, number, variance. Mean.
Yes.
Okay, so I think we can resume. Gabriela is connected, so I think we can start. So we are starting now the more detailed session on specific project. Next speaker is Gabriela Sopardi from CERN. And so she has a PhD in computer science, and she's been working with the collimation team at CERN for the past 5 years. She's the primary software developer and contact person for the controls of the collimators in the LHC, and which are meant to provide the protection of the machine. And she led all the collimator alignments of the LHC operation, and she's now the primary coordinator between all the teams involved in collimation. As a side note, she was also involved in one collaboration CERN had with the World Health Organization and the UN on developing tools to model the airborne transmission of COVID recently. So she's very much into data analytics. And also, Gabriela, if you can share your screen, your presentation.
Thank you, Manuel. I'll share my screen. You should be able to see it now.
Yeah, perfect.
And can you hear me clearly?
Yeah.
Okay, perfect. So hello, everyone. I will present how we can apply an LSTM to automate the alignment of collimators. So I'll start from the very beginning. Basically, the collimation system provides passive protection for the LHC. We can see here we have all the collimators around the LHC ring. At the start of run 3, we will have 123 movable collimators. Here we have an example of a collimator. It's made up of 2 jaws that are positioned around the beam axis. And basically, we need to align the jaws to step precision of 5 micrometers in order to concentrate the beam losses into the warm locations. Each year of operation, we begin with a commissioning phase to align all the collimators in order to ensure the correct settings for operation. We perform collimator alignments at all machine states. So when we inject the beam, when we ramp up and then reach top energy at flat top, we align the collimators during squeeze and in collisions. In order to align collimators, we have beam loss monitors. These are a type of device that we have available to us. Here we can see in yellow, this is the beam loss monitor that's installed outside the beam vacuum. And basically each collimator has its own respective beam loss monitor further downstream in order to record the beam losses generated by the collimators as they touch the beam. We refer to the alignment of collimators as the beam-based alignment, BBA for short, as it requires the beam. So I'll talk a bit about the beam-based alignment. So basically, as I said, we have the collimator and we have the respective beam loss monitor. If we look at the losses in the beam loss monitor, we can see that they're steady because the collimator is far away from the beam. So we have low losses and steady losses. Once we start moving the collimator towards the beam, the showers are detected by the beam loss monitor. We can see when the collimator touched the beam, we can see that there was a rise in the losses. So basically, we need to move the jaw towards the beam until we see this loss spike shape detected in the BLM signal. We then wait for the loss spike to decay between alignments, and then we can start the alignment of either the other jaw or the next collimator. So in this case, we would move the next jaw, and we would wait again for the same signal in the losses. Now, a complete alignment campaign can produce more than 1,000 observation spikes. So this means more than 1,000 alignments. Now, without going into much detail, but to give you an idea of some numbers, here we have the number of collimators that we align during all alignment campaigns at all machine states over the years, during commissioning at the start of the year, and any reconfiguration throughout the year. This also excludes any particular alignments that we would need to set up for machine developments or some operational tests. But basically, we align hundreds of collimators each year. And aligning each collimator with BLMs requires multiple alignments. So for example, in 2018, it would take around 8 alignments per collimator to align each collimator. Between 2016 and 2017, it was around 25 alignments per collimator. And then before that, it was more than 25 alignments per collimator. And the reason for this change in the number of alignments required is because we've had upgrades in the software to improve the alignment. So this is to give you an idea why we have so many alignments, and for each alignment we have an observation spike. Now, what exactly are these observation spikes? So as I said, we move the collimator towards the beam until we see a loss spike in the losses. So these in green here, these we call alignment spikes, which indicate that the collimator has touched the beam. Whereas these the green ones on the left. Now the red ones on the right, these are spurious spikes. These are losses that were not generated by the collimator, but by other factors in the LHC, which means that the collimator has not yet touched the beam and must keep moving towards the beam until it can finally touch the beam. So a quick recap on the alignment software that we've been using. Since 2011, we've been using the semi-automatic alignment. So what does this mean? It means that the user first selects the collimator to align, selects a BLM threshold to stop the jaw movement, which I will explain now. Basically, the collimator automatically moves towards the beam until the losses in the BLM exceed the threshold here specified by the user. Once the losses are exceed this threshold, the movement of the collimator will stop. And then the user comes back in to determine if the collimator is aligned or not by looking at the BLM signal to determine if there's an alignment spike or a spurious spike. So as you can imagine, when we align a large number of collimators, we also require a number of collimation experts to align all of the collimators. Now, since 2018, the alignment has been fully automated. So you can see here, I've automated all the steps in the collimator alignment procedure, with the key underlying factor being the use of supervised machine learning to determine whether the collimator has aligned or not. Now, I will talk a bit about the supervised machine learning. So basically here we have a data sample, we have the BLM signal, and we have the collimator position. So we can see the collimator, it's moved in, and at this moment in time, it created a spike, so the collimator stopped moving. And at this point in time, we wait a fixed, with the supervised machine learning, we have a fixed waiting time, which in this case is 4 seconds at injection and 6 seconds at flat top. So in this case, it's 4 seconds, so it's at injection. Once the 4 seconds pass, I extract 5 features, which are the spike height, I fit an exponential decay to the losses, to the loss decay, and I take the jaw position in sigma. And using these features, I can classify using supervised machine learning whether we have an alignment spike or not. And actually using these machine learning models, I managed to achieve a precision of over 95%. And when using the machine learning and the other algorithms to fully automate the alignment, I can show you the results we achieved. So basically here, we have the time taken to align the collimators at injection over the years. We can see in 2010, it would take 20.5 hours to align the collimators, whereas in 2016, 2017, it seems with the semi-automatic alignment, we seem to have peaked to just under 3 hours. Now, with the fully automatic alignment using machine learning, we've managed to further decrease the time, and we can align 79 collimators in 50 minutes. And actually, I had presented this work up until here at the last machine learning and data science workshop at ICALEPCS 2 years ago. So what have I been working on since then? So basically, since we used it for the first time in 2018, I wanted to take a closer look at how it actually performed by comparing the parallel fully automatic alignment of 2018 to the semi-automatic alignment of 2016. Here we can see the number of collimators that were aligned. We can see that the time has decreased from 2.5 hours to 50 minutes. We can see the moving time here, the total alignments required. And actually what's interesting is that the moving time of the collimators is consistent at 38%. So this tells me that I can further speed up the fully automatic alignment by decreasing the time waiting for the signal to decay before extracting the features. If you remember earlier, I said that at injection wait 4 seconds and at 6 seconds wait, and at flat top wait 6 seconds before predicting whether it's an alignment spike or not. So in order to increase the moving time, we need to decrease the waiting time. So I wanted to analyze a bit the actual time required for the BLM signal to decay once we have an alignment spike. So what I did was, here we can see the BLM signal in blue, and I put an exponential falling distribution to model the decay rate, such that I'm using that the optimal losses are achieved after 6 half-lives. And here we can see with the purple line that the losses have decayed, and at this moment they've decayed enough in order so we can start the next alignment and generate the next spike. And actually, if we look at the overall results, we can see that in gas injection in green, most of the samples have already decayed by 4 seconds. And similarly at flat top in purple, most of them would have already decayed by 6 seconds. And actually the mean decay time is 0.61 seconds at injection and 2 seconds at flat top. So the proposed solution is to train a long short-term memory model to continuously classify the spikes in real time and automatically adjust to the spike decay length. So from the data that I have between 2016 and 2018, I have 3,000 observation spikes. And over here, I worked with a master student from Rome, where he basically tried out different variants of the LSTM until we converged on this particular architecture that can work for us. And as an input, we converged on using the BLM signal scale with the collimator position sigma and z-score as the normalization technique to rescale the features. So using this LSTM, and then I collected some results over a 10-fold cross-validation, randomly stratified 30 times. And here we can see that over 75 epochs, we achieved the optimal training. And actually, I have an average of 94 precision achieved on the testing sets. Now, I keep mentioning precision, and the reason I'm using precision is because we want to avoid false positives. So basically for us, if we falsely detect an alignment spike, it means that we're misaligning a collimator. Whereas if we don't detect an alignment spike, that simply means that the collimator jaw will move slightly further in until we finally detect an alignment spike. So for us, false positives are much more grievous than false negatives. So the way I actually calculated this precision, this 94% here, is by evaluating the classification probability at the end of the available sample. So as I showed before, I have this particular sample. Now in this case, I was taking the classification at the very end of the sample. And if the classification score is larger than 50%, then I can classify this as an alignment spike. But this is not what we want. We want to use the LSTM to already predict at this purple line over here. Otherwise, we're still going to end up waiting the same amount of time. So I had to analyze this further to determine the best moment to predict the spike loss and the ideal probability thresholds to possibly improve the model's precision. So the first thing I analyzed was I used the LSTM to continuously classify each sample at each time step. So here we can see if the LSTM starts classifying, it starts at less than 40% for both spike classes. However, as the BLM signal moves along, we can see that the alignment spikes, it becomes more sure that it's an alignment spike and more sure that it's a spurious spike. And we can see that at 1.5 seconds, there's a clear distinction already between the two spike classes. And actually, if we look here at the rate of change in classification, we can see that the spurious spikes are quite steady, so there's not much change. And the largest change happens at the beginning for the alignment spike class. And actually, at 1.5 seconds, we can see that the rate of change of classification for the probabilities of alignment spikes falls below the 0.2 threshold here. And if we take a closer look at the 1.5 second point in time here of the two spike classes, we can see that there's no overlap between the two spike classes at 80%. So then I wanted to analyze further the latency required to obtain the maximum probability per spike class. And so here what I'm plotting is the maximum probability achieved by the two spike classes and the time required to achieve the maximum probability. And what this shows is that 98% of the spurious spikes obtain the maximum probability within the first 1.5 seconds, and all of the spurious spikes never exceed the 80% threshold. So from all of this analysis, I can conclude that I can use the LSTM to classify when the probability gradient is less than 0.2, which takes 1 to 1.5 seconds at injection. If we look here, when it falls below 0.2, we can see from the standard deviation that it starts off at 1 second to around 1.5 seconds. And we can classify spurious spikes when the probability is less than 80%. At this point, if it's a spurious spike, then we can just begin the next alignment. However, if it is an alignment spike, so it's greater than or equal to 80%, then I suggest to fit an exponential function to determine when 98.5% of the BLM signal decays, as I had shown earlier. And on average, it would have already decayed, because if you remember, the mean was 0.61 seconds at injection. So based on this analysis, I classified the BLM signals using the LSTM model, and actually this increased the precision on the dataset to 98%. So then I wanted to analyze the time taken to actually classify the BLM signals at the two machine states. So what I did was, when the collimator stops moving, I wait 1 second at injection, and I start the LSTM classification. And actually the mean time is 1.07 seconds at injection, and the maximum time it's required was 1.72 seconds. And at flat top, I waited 1.5 seconds before starting the LSTM classification. Again, the mean time is similar to this, and it's actually required 2 seconds as the maximum time required. So looking at the mean time, this is a factor 4 speed up compared to the present implementation with the supervised machine learning, which is 4 seconds at injection and 6 seconds at flat top. So I'm not going to go into the details of of the procedure to align a collimator, but here I'm showing the time required to align the collimators using the fully automatic alignments with supervised machine learning. And the variable here is the time waiting for the losses to decay, which is X. So as I said, it's 4 seconds at injection and 6 seconds at flat top. And now with using the LSTM, it's capable of dynamically classifying the spikes at times of varying lengths. So this X will now change to 1 second and 2 seconds at flat top for detecting alignment spikes. And then for detecting spurion spikes, it's again 1 second at injection, however, 1.54 seconds at flat top. These are from the previous slides. You can refer back to them later. So I wanted to compare and then different cases of alignment. So we align, for example, one collimator at injection using the supervised machine learning. It would take, so this is calculated from the table on the previous slide. It would take 53 seconds to align a collimator, whereas with the LSTM, it would take 27.5 seconds with the LSTM. 79 collimators at injection, 71 minutes using the supervised machine learning, and again, 36 minutes using the LSTM. Same one collimator at flat top and 79 collimators at flat top. And then I also included, so these 4 cases assume that every alignment that we have resulted in an alignment spike. Of course, this is not the case. We'll have to go through some spurious spikes before actually reaching an alignment spike. So I also included a case of if we encounter a spurious spike for each of the alignments required for a collimator. And this increases the time, and then, as you can see here. So actually, this results in a 50% speed up using the LSTM. And actually, this is to align the collimators sequentially, whereas when we align the collimators in the 2 beams in parallel, as I mentioned before, we aligned 79 collimators in 50 minutes at injection. So using the LSTM, theoretically, we could align 79 collimators at injection in just under 25 minutes. So to summarize, we have 123 collimators in the LHC that we already automatically aligned since 2018 using supervised machine learning. And after analyzing first use performance, I identified a bottleneck caused by the fixed observation window used by the supervised machine learning. So I trained an LSTM model to continuously classify the BLM signals, and it is able to classify the spikes within the first 1 or 2 seconds based on the machine state of the collimator stopping its movement. And following each alignment spike, as I said, my suggestion is to fit an exponential function in order to determine whether the losses have decayed or not. So the splitting between independently classifying the BLM signals and of whether the losses have decayed or not, we can actually decrease the alignment time by 50%. And finally, the LSTM model is already readily trained and available to be incorporated into the alignment software for testing during the LHC Run 3 next year. Thank you for your attention. Let me know if you have any questions. For more detailed questions, I'm around throughout the conference. I have a presentation on Wednesday for detailed questions on the fully automatic alignment, and 2 posters on Thursday on the machine learning and all the controls for collimation during Run 3. Thank you.
Many thanks, Gabriela, for this very nice application of machine learning with actual results. This is also something very good to see that there are actual results coming out of this. And also you've shown the evolution applying different techniques. So this is very nice. So are there any questions to Gabriela? No? I would have one maybe very theoretical, because I think the automation you have achieved is already quite impressive. Probably there's no need for going further in the automation. But imagine you wanted to go further, or you would need to go further. Which would be the next step you would use to reduce even further the time it takes to do this?
So the next step is I will share a different part of the screen. So I will share this now. Okay, so as I mentioned here, I fully automated the alignment by automating the selection of the BLM threshold, the collimator, determining whether the collimator is aligned or not using machine learning, and selecting the collimator. So these are all three different ways, three different sort of modules that I automated for this. And the next step would be to actually tackle how we select the collimator. Because basically the reason we need to see how we select the collimator to align is because when you align a collimator, its losses are detected by multiple BLMs around the ring, not just its own dedicated BLM. So this is what we call crosstalk. So you need to select collimators that don't have crosstalk between each other, so that you can actually associate the alignment spike with the collimator that's actually moving. So the way this crosstalk is implemented can definitely be improved. And also, what I want to look into is, rather than only aligning one collimator from beam 1 and one collimator from beam 2 in parallel, we might also be able to align maybe two collimators from each beam from different planes. So we have horizontal, vertical, and skew collimators cleaning in different planes. So if we manage to, we've never done this before though, because it was very complicated to determine manually which collimators don't have crosstalk and which don't. But now that we have the full automation, we can definitely look into these possibilities of sort of selecting more collimators that we can align in parallel, and being less rigid in the crosstalk, and maybe also filter out the crosstalk to align even more collimators in parallel.
Okay, and which techniques you would use for that? You have already ideas on that, or?
I don't right now. I don't really have much to go on, because this is quite some new studies. What I can show is that I have a heat map. So this is what I have so far. Basically, here we can see the effects of the collimator aligned in beam 1, for example, and their effect on beam 2, and vice versa. But this is only when we're moving one collimator and the effect on all the others. As soon as we start moving multiple collimators, the effect on other collimators will change again. So this is something that no one has actually looked at before in detail, and we need to see how to tackle this actually.
Okay, nice. If anybody has any idea how to solve this,
I'm open to ideas.
Okay. If more questions to Gabriela, or solutions, maybe not questions but answers. No. Okay, so thank you, Gabriela, again, and
thanks, Manuel.
Next speaker.
Okay. So in the last 2 years, a few workshops took place in Europe about machine learning. One of them is being organized by the ICALEPCS. So this talk is given by Danilo Ferreira de Lima, who is going to report on this workshop. Danilo has a PhD in particle physics at the ATLAS experiment, working on top quark, Higgs boson, and jet substructure physics for many years. Recently, he has switched to focus to machine learning, and now he is part of the team at the ICALEPCS, together with Artman Davkan and Luca Gelisio in the data analysis group, applying machine learning techniques to improve automation, data mining, and enable new science. So please, Danilo, you can share your presentation.
We don't hear you very well, I think, Danilo. Maybe it's only me, I don't know, but we hear you very.
Your mic is on, but maybe it's not the right mic.
Is that better?
Yeah.
Okay. Sorry about that. So if you can you just confirm that you can see the slides properly?
Yes.
Yeah, good, thanks. So first of all, this presentation was supposed to be given by Ahmed Davtyan, but there was this unfortunate accident that his wife gave birth recently. So I'm substituting him, so just to mention that it was supposed to be him here. We recently organized a workshop and basically want to tell you about this because perhaps there's not so much looking at the agenda, there's not as much crosstalk between current physics that's going on in, for example, the LHC and our experiments and photon science. And we wanted to basically tell you that we exist. And in this workshop, the topic to be tackled here is that there are new emerging technologies in machine learning and in photon science. With the European XFEL, we have a huge amount of data that's been collected in a very short amount of time. And that is, while that's relatively common, for example, in particle physics, that has not been so much in photon science. So we have to adapt the entire machinery to tackle this high rates. So we organized this workshop on the 8th of June. That's an excerpt from the agenda. And we had 14 speakers and 160 participants. We discussed supervised and reinforcement learning, and we tackled different domains, going from single particle imaging data collected in our experiments to orbit optimization, automation of the analysis, reconstruction of the XFEL process, and object detection to do phase retrieval, and automation of the beamline operation. So there is really a lot of topics which are using all the machine learning techniques, and perhaps some of these methods you are already using in your team, and we didn't think about it, and some of those maybe we thought about it, and you might take advantage in a completely different scenarios. And that's why we wanted to have this workshop to brainstorm on other ideas. One example, I have a few slides from talks, which are not mine, from this workshop, just to give you a taste of what we discussed. One application was on machine learning. We have this frequent problem that we have a beam here. It's an X-ray free electron laser. We inject some particles here and some molecules, biological matter, depending on the case. And we basically have a detector here that detects the photons after collecting diffraction pattern. Now, in this particular example here, we are looking at single particle imaging. And in some cases, you might have two particles simultaneously being detected. Here's an example with a single particle diffraction pattern and double or perhaps more diffraction pattern. And we have to separate those. But different from several of the talks that we have here today, or at least from what I could gather, there is no label. We never have any labels. In this example here, someone had to manually go there and manually label each one of those images by looking at them, and then use machine learning methods. So this was YOLO. It's just a very, very large convolution neural network to identify the hits and estimate which ones of those are single hits and double hits. And of course, we can only estimate which ones are correct and which ones are false within the labeled data set. But this can then be extended and applied to a larger data set, which is unlabeled, for us to have an automated system to select single hits. And these single hits are what the analyzers want. The double and triple hits are quite problematic. We cannot analyze them. This, by the way, this was given by Alexander Ignatenko, and it was also published here in this paper. Another example of what we discussed is how to actually cluster the images. As I said, the big problem we have is that we don't have any labels. So what do we do with those diffraction patterns when we don't have any labels? One idea from Julian Zimmerman is to use a variation autoencoder to project that information to a latent space, which is required to be shaped as a spherical Gaussian, and then decode this latent space in each one of these components that he obtained to obtain fundamental images that could explain the composition of an input image. And that's what he gets. And from this, he can see that an image could be composed of several of those diffraction patterns, which have different distances between the rings and different shapes. Right? Not all of them are symmetric. So using that, you can extract some information and categorize perhaps your data now in the latent space, not on the image space, which has millions of pixels. Another example on how to use machine learning in photon science is given by phase retrieval. In phase retrieval, I will just quickly explain in case some of you don't know it. What happens here is that we again throw the laser beam on a particle, the X-ray laser beam, and what we collect is a diffraction pattern, which is a slice, a 2D slice of this 3D image here. This 3D image is a Fourier transform of the real pattern, but we would like to have that Fourier. We would like actually to have the inverse Fourier transform of that, but we only see a slice of that, a two-dimensional slice of that. So the question is, how do you get this 2D slice and transform that into the actual 3D representation of a true real space particle, which could be, for example, a lattice structure from a crystal, or even a DNA structure. In the latest experiments, there was, for example, an experiment trying to examine the COVID virus. So to actually, the problem with this entire process is that you lose the phase information from this Fourier transform, and inverting that from the Fourier transform to the actual real space involves two problems. The first of them is that you only have a 2D slice of this. The second is that you don't have the phase of the Fourier transform. And in this example here, a long trained a convolutional neural network, which recovers both the phase and the intensity, which is much faster than traditional methods to do this, which should simply use an iterative approach and to try to assume certain symmetries in the object to try to recover the phase, which mathematically is a very hard problem. So this is just 3 examples of what was discussed in the workshop. People were very interested in moving forward and using machine learning in this field exactly because of the large amount of data that we're collecting now. All of them are moving ahead and trying to take advantage of these new methods and discussing how to use them reasonably. One example of what we in our group are doing is that we often collect some data, and if you put a high intensity beam on some of the samples, especially biological samples, you destroy the sample. In some cases, that's the objective. We want to destroy the sample because we don't care what happens afterwards. But in some cases, we don't want to destroy the sample, or we can somehow destroy a crystal if the intensity is too high. But if you don't have a high intensity beam, you can get an image that looks like this, which is not the ideal. So what we can do is use a generative adversarial neural network to use non-paired samples of images to get an image that is much higher resolution. This one, for example. So of course, this training image has no relationship with this one, but the gun can learn from this to extrapolate what would be the correct image corresponding to this one. if we had high intensity beam without actually destroying the sample. And this image in the bottom is a cut done across this diagonal, showing the pixel intensity across this diagonal. And you can see that the blue line shows the input image, which is pixelated, and the output image is closer to the high resolution one. This is very early work still, but you can see that there's significant improvement. The question here is how to incorporate uncertainty to that, because clearly there are regions where this doesn't match at all very well, and incorporating uncertainties here is very important. We also have other things I'm going to present. The next presentation is on a different topic, automatic parameter tuning, which is also working in our group, and it's a bit more advanced than this study. So this is the data analysis group in the UXFEL. We have people with a very diverse background, physics, engineering, computer science, chemistry, and biology. We would like to let you know that we'd be open for collaboration, and if you want to brainstorm new ideas, we are here. That's it.
Thank you for your interesting presentation and workshop. Okay, I have one. Or maybe are you going to repeat this workshop in the next future?
Sorry, can you say that again? The sound cut a bit.
This workshop in the next years.
If you're going to repeat it in the next years, we do plan to do other versions of the workshop. It's not clear if it's going to be the same content, but we do plan to have other workshops. We don't have yet a date or anything like that, but it is the intention. Yeah.
If there are other questions, I have a quick last question.
Marco, I think there's a problem with your sound. At least I don't hear you very well. I don't know if the others have the same problem.
Yeah, I have the same problem. I thought it was on my side.
Try to. It seems to me that it's better.
No. Maybe you can place the question on the chat, or because Danilo is going to have another talk now, we can take the question after the second talk. It's a bit better. Can you talk a bit more?
Hear me now? Is it better?
Yes. Yeah, much better now. No. No.
Okay. Can you proceed with the?
No, it's okay. No, it's okay. Okay, maybe let's continue, Danilo, with your second presentation, and then let Marco get of his mic problems.
Okay.
So
to talk about an experiment applied actually to the automatic tune of input parameters in an experiment using serial femtosecond crystal.
yeah, we still didn't hear you very well, Marcos. Danilo, maybe you can proceed with the presentation.
Okay. Yeah. So so this is a quick summary of this of our development of our study on a method to automatically adjust some parameters of tools that extract information from crystallography results. Since the audience here is not necessarily filled with people on photon science and crystallography, as far as I understand. I'm going to give a quick summary of the concept. In stereophoton spectrum crystallography, what we do is that we get crystal or nanocrystals, inject them with a liquid jet here, and then we throw a laser beam at it in the UX fan, and we collect data from this crystal, and we're going to see several diffraction peaks, several Bragg peaks here, which corresponds to the Miller indices of that crystal. Of course, these crystals have random orientation. We don't know which direction they're coming, but we can use that to recover the orientation. We can use the position of those Bragg peaks to recover the orientation and the intensity of those peaks to estimate the intensity of the electron density function inside of the crystal. And one example of how that can be used is that you can freeze a piece of biological matter inside of a crystal structure, and you can estimate the electron density of that biological matter within that crystal. The problem with this method is that people often collect here millions of frames, millions of images. You have then from millions of images to identify these Bragg peaks, which are just a single pixel, which have a very high intensity over a background noise. We identify the Miller indices corresponding to the crystal to the peaks and the crystal orientation, and then you integrate the intensity of the Bragg peaks. All of those steps require a set of parameters. How big are your Bragg peaks? How intense would a peak be for you to consider it a true Bragg peak? Which kind of how much is the level of noise that you're willing to accept? All of those minor parameters which you need to set, and they make a huge difference on whether you can collect some information from that data or not. So can we automatize the parameter tuning, still keeping this tool which is strongly based on physics knowledge, the same way as it is? So the way we want to implement this is by taking a data stream that's arriving, and while it's arriving online, we feed part of this data stream to a reinforcement learning algorithm. This reinforcement learning algorithm is trained for a few episodes to try to identify the best parameters for this tool. And then at some point, we update this tool, which is called Crystal here, with a new set of parameters. With those new set of parameters, the next data that's arriving here are going to be are going to have a better performance in the identification of the orientation of the crystal, in the identification of the good frames that the user would be interested in. Now, the way it works is like this, and I'm going to just introduce some nomenclature for reinforcement learning for people that are not used to it. Here, just for context, here we are using a model-free hectocritic model of on-policy reinforcement learning. All of those words mean something particular. So it's model-free because you're not assuming anything on the behavior of the system that you're controlling. It is hectocritic because it uses an hectocritic model, which I'm going to introduce next. But more importantly, it's on policy. So here, for example, we do not rely on the Bellman equation, which was introduced before in the previous presentation. We optimize directly the policy of the agent. The agent performs an action in the environment. We collect results. We give a reward to the agent, and we try a new set of parameters. So each time the agent does an action, meaning changes the parameters, that action is done with noise, the exploration noise, to try to vary parameters within some range. And after it learns, it can update the agent without this noise so that we have a new set of parameters that is the true best so far. The objective of the reinforcement learning is to optimize the returns, which is the sum of rewards weighted by this gamma. And this gamma is reweighting how much we want to forget the past, because gamma is a number between 0 and 1. So what we do is that we do that exact same procedure, but with CRISPR, which is this crystallography tool. the environment is basically these two. The actions are changes in the parameters in Christopher. The state in reinforcement learning are going to be the current set of parameters. The rewards are going to be the change in the fraction of images that have been correctly indexed. And a positive reward, therefore, means that we have increased the amount of images correctly indexed. A negative reward means that the agent should be punished for taking the wrong action. The agent is just a parameterized function, and because of Sebenko's theorem, we can use a neural network for that, only because Sebenko has proven in 1989 that a set of a function that has this topology, which is exactly a neural network, a single layer neural network, can reproduce any function given that you give it enough number of parameters. Now, this is an actor-critic model, and the idea of this actor-critic model is that a critic is going to learn some auxiliary function, V, which I'm going to call here which is often called the value function. In this case, it learns this function A of S, which is the so it tries to learn this function V, which is supposed to be the returns G that I mentioned before, and therefore the critic's objective is to minimize the mean square error on the return that it predicts and the true return, which is what you see here in the slide. The actor, on the other hand, is going to try to, knowing what the critic's telling it, which is to the future return, it's going to try to use that to find the optimal set of state parameters, which can optimize the future return. And what we are using here, what we saw that was the best method for us, is to use this advantage actor-critic model and actor. And it's based on this theorem from Williams, 1992, which showed that although we cannot directly calculate the gradient of the returns to optimize the returns, we can calculate this quantity, which is the average value of the gradient of the log of the probability of the action times returns. That is an unbiased estimator for the gradient of returns. And that theorem from Williams is very strongly used in on-policy reinforcement learning. The only difference in this, there are many variations. The variations are how to slightly tune that optimization method so that you achieve the goal faster. In actor, for example, we use a second-order optimization algorithm to improve convergence speed. But the main idea from 1992 remains the same for on-policy algorithms. Using that method, we try to use the reinforcement learning on a biological sample of hen egg white lysozyme collected in the SPD experiment here in the UXFL. And we try to do that with 10 parallel cores. The reinforcement learning algorithm is very fast. It takes 1 second out of 1 minute. Most of the time is spent on the analysis itself. And the fraction of indexed images that we see with Christopher, if we do nothing, it would stay in this red line, so around 6-7%. But by taking the reinforcement learning action, the fraction of frames, of good frames, so indexed frames, increases from an initial value of 6% more or less to around 10%, doubling the amount of the collected amount of data. And here you can see one of the parameters we're tuning, which is called the minimum, it's the mean SNR, so minimum signal to noise ratio. And as the time evolves, it tunes to around a value of 5.5, which is a bit better. Some other tuned variables, you can also see some other tuned variables. Here's the minimum pixel count to identify a break peak. This one is the distance, it's adjusting the percent value of the distance between the detector and the sample. We also tried the stability test on which we initiate the optimization already in an excellent optimal position. Well, not optimal, but optimal as far as we know. And check if the machine learning tracks, so it doesn't change anything and worsen the situation. And it seems to follow more or less the same no action line. So in summary, We are using on-policy reinforcement learning algorithm to optimize the SFX, so serial intersecting crystallography pipeline online, so that the user can get an immediate result when he's collecting data, he or she. And there we have a clear goal: maximize the number of indexed frames, and maximize the number of frames which are identified as good for the crystallography analysis. And we had tested the system offline, and we have further tests on new data sets coming, which are perhaps a bit more challenging, so that we can check if the system works with more complex data. And that's it.
Thank you very much. Can you hear me now?
Yes.
Okay, that's good. Thank you very much, Danilo, for the interesting talk, and open for questions.
I have one if nobody else has, but maybe we're hijacking. So Danilo, compared with the problem that Gabriela presented before, I understand here there is no need to have like a memory of what happened in the past. No, this is why you are only using reinforcement learning. You don't need some kind of memory.
So yeah, exactly. We tried also some other off-policy. So let me just explain what you're saying. It refers to off-policy algorithm. In off-policy reinforcement learning algorithms, you have a memory of the old data, and you queue the old data in that memory. Sometimes you throw some data away from that old memory. When you use that memory to train the reinforcement learning algorithm, that works well with off-policy algorithms. For example, DDPG, TD3 are examples of those algorithms. But those algorithms have some limitations. One of them is that they tend to be more unstable in some cases, not always, because they rely on the self-consistency of the Bellman equation. Because the Bellman equation only guarantees that when the Bellman equation is satisfied when you are in the optimal situation. If you are always closer to the optimal as far as you know at that moment, that's great. But if you're very far from the optimal, if there's some unbalance, that can lead to instabilities in the algorithm. So that is a problem with the off-policy reinforcement learning. And the algorithms that I'm presenting here now do not have that problem. So this is an advantage for these algorithms. On the other hand, the algorithms that I'm presenting here, which are on policy, although they have this advantage, they are much, much less data efficient. That is, if you use those algorithms, on average, you would tend to take more time to realize a change in the environment, if there is one, or if there's a change in action that needs to be done to control the environment, that is. The lack of memory is exactly what makes this a bit better in terms of stability, but we lose data efficiency. So that's there's no free lunch effect here between those two kinds of algorithms.
Okay, thank you for the explanation.
Okay. We have other questions for Danilo. So if not, we can thank Danilo and for the two presentations. And the next talk is about the report of another workshop. In this case, it was organized under the umbrella of the LEAPS European project. The speaker is Marco Calvi. Marco is an accelerator physicist working since 2009 at PSI. After his PhD in 2004, he started his career at CERN in the domain of high-field superconducting magnets for LHC. Then he joined the ITER project for the test of superconductor tokamak cold cables. At the beginning of the Swiss FEL project, Marco worked on the ondulators, and today he is an experienced physicist in the domain of synchrotrons and free electron lasers, specialized in high-temperature superconducting ondulators. Let's see that you are ready. Please go. Can't hear you. From time to time we hear, but not continuously. Oh, okay. Automatic level control. No, we cannot hear.
We don't hear you, Marco. We don't hear you. We cannot hear you. No, we don't hear you.
Can you hear me now?
Yes.
Yes. So we have to choose either the sound or the video. We cannot have both. No, we don't hear you.
Let's try to speak, Marco.
Sorry?
Can you say something, because it's not sure that we are. No, doesn't work.
You.
Now we hear you. No, we don't. We don't hear you now.
No, can't hear you. So Marco, if you want, we can proceed with the next speaker, if available, and then we can postpone your speech after that.
And maybe Marco tried to connect and reconnect again.
Yeah, maybe it's better.
Maybe that's well, and then we move to Leander, which I think he was asking me first, but I think he's connected. Yeah, see him there. So Leander. So Leander is going to tell us. So Leander is currently completing his PhD in computer engineering. He's working on the renovation of the beam-based feedback system of the LHC, with a focus on the application of machine learning techniques for that problem. And so he's going to tell us today about the machine learning for the tune estimation in the LHC. So Leander, if you can share your screen. And I don't know if the sound is working.
Can you hear me?
Yes.
Sorry, but I cannot hear you.
No, you cannot hear us?
Okay, okay, because I cannot use the headphones. Anyways, I can start anyways. So, share my screen.
We don't see the screen yet.
Yes, I'm coming. Okay. So I think you can see it now, no?
Yes.
Yes.
So I'll be talking about, Veren already mentioned this work. So here I'm trying to apply machine learning for the tune estimation in the LHC. So for those who are not familiar with the tune, it can be defined as the frequency of the beta oscillations. So these are the transverse oscillations in an accelerator and a circular accelerator. The baseband tune system was responsible for estimating the tune in the LHC, and it's known as the barbecue system. And it obtains time series data, which is sampled at the LHC revolution frequency, using this circuitry, which is then transformed to a frequency spectrum using fast Fourier transform. And after this, an exponential moving average with respect to the frequency bins is passed over the spectrum to smoothen it. And then there is an algorithm which is called the BQ algorithm, which was used until run 2, which was responsible for estimating the position of the peak that is seen in the spectrum. So the tune would be equivalent to the position of the peak within this frequency window. And the old algorithm was trying to do this algorithmically by applying a series of median and moving average filters, and then estimating the peak, going back to the original and doing some tricks like this to try to improve the accuracy. However, it was observed time and time again that it was susceptible to these 50 hertz spikes that can be seen in this spectrum here. So problems from the start, which were due to these 50 hertz noise harmonics, which were observed in these spectra. So here is a heat map. The y-axis is the frequency. The x-axis is the evolution of this frequency spectra. And these harmonics create these spikes, which make it very difficult to estimate the peak of the spectrum. Simply by being there. They're always there, and they were not removed so far. So what was happening exactly with the old system? Well, these estimates, they were exhibiting a very large variance at times. Here we can see that the estimates were jumping by more than 100 hertz. They also had a tendency to get stuck, these harmonics. So if you're trying to estimate the position of the peak, but you're always estimating the position of the noise, then that's clearly not a good estimate of the tune. And finally, it was sometimes really clear that these estimates were jumping from one peak to the other. I'm sorry I did not explain these plots, but here these squares are, the colors are corresponding to these axes in the bottom, and the top plot is showing the tune estimate. Y-axis is frequency, x-axis is time. So we can see that it's getting stuck to one harmonic and then jumping to the other. So different algorithmic approaches have been attempted to try to mitigate this problem. And the most straightforward way was to intercept the location of these harmonics and remove them from the spectrum. And this would create spectra with gaps, such as the one shown on the top right, where the blue is the original spectrum. And by removing these noise harmonics, you can try to estimate the tune using only the orange points here. A series of algorithms were attempted: Gaussian processes, the weighting moving average, and the polynomial fitting. And the performance was somewhat improved. However, the simplest algorithms to implement, the WMA and the polynomial, they were the most sensitive to hyperparameter tuning, which means that you can get different estimates depending on the type of spectrum. And the Gaussian process is very computationally expensive to do in real time, because you have to invert constantly a 100 by 100 matrix. The 100 comes from the size of the input spectrum. And you have to do this at 12.5 hertz. So it is possible. However, it's very expensive for this simple computation. Tuning the harmonic removal was also proved to be tricky. So these harmonics, as was in the previous slide, they are not exactly 100% stable. They might change a bit. And this might affect their interception and their removal. So this approach was deemed a bit difficult to make it work. So we go to the first approach that was attempted with machine learning, which is the naive approach, where we just have this real data set, which is made up of these logged barbecue spectra. And along with them, there's the tune estimates, which were made by the BQ algorithm, so which we know are wrong. However, in the beginning, we can try to train a deep neural network or a 1D convolutional neural network, where the input is the normalized barbecue spectrum, and the label would be the tune position, normalized from 0 to 1, relative to the window, to the input frequency window. So you would expect that you would have correct tune predictions, right? But the naive approach is too naive, simply because the log barbecue spectra do not have the correct labels. And the log tune estimates come from the BQ algorithm, which we are trying to replace in the first place. So instead of using this real spectra, we can try to simulate spectra. So as done in this paper, which introduced the alternative approaches, we can try to use a second order system simulation. And there's an example here where these are two examples of real spectra. And superimposed now, we can put these simulations to show that with these 50 Hertz harmonics, so these were examples which I found which did not contain these harmonics. And we can see that this simulation more or less creates spectra of a similar peak and a similar shape, and we have complete control on its width and its position. So the second machine learning approach is the simple approach. They were very ad hoc names here, where we can create a simulated data set. We can do a Monte Carlo simulation to create many different types of spectra. We can inject these 50 Hertz harmonics with random amplitudes ourselves, so we can get something which looks real. And then we apply digital filter to make them a bit wider, as are observed in reality. So here we're seeing that we can tune our simulation to make it look real. So this is an explicit way to try to go nearer to reality here, where the blue plot is an example of a real spectrum, and the red plot is showing this a simulation where the position and the width of the peak were calibrated by hand just to show that the simulation is able to create something similar. So the same approach to the naive approach can be attempted, where you can train a deep neural network and 1D CNNs with different architectures. These are the hyperparameters of those networks that were tried. So this is a hyperparameter grid search sort of. And the evaluation of the simple approach, we can do it by getting the predicted tune. We subtract the ground truth tune, which we know because it comes from simulations. It was done over 5,000 spectra, and it was seen that the algorithmic approaches had significantly more error than these simple approaches on simulations. However, they were promising, but when attempted on real data, obviously these, as can be seen here, they behave no better than the old algorithm. So simply by using simulated spectra to train these models is not effective. So here I show another metric that we can assess these models trained in the simple approach. This is a metric used by the tune feedback, which looks at the amount that the tune changes, the amount that adjacent tune values change. So, and it's an exponential moving average of this difference between adjacent tune estimates. The tune feedback had two separate stability metrics, one which was operating at 1 second time constant, and the slow one was operating at 10-second time constant. We can see the BQ algorithm. This is a probability and density graph showing the expected error, the expected stability when we use the BQ algorithm. So here I got a real data set and try to obtain these plots. But we see that the CNN approach, which is ML5, this is the best CNN. Its stability metric is all over the place. And also, if it surpasses this black dotted line, it means that the tune estimates are too unstable to be used by the QFP. So this was something that was used in operation to safeguard the operation of the feedback. And the DNN, the best DNN model, was a bit better than the CNN, however, still not better than the BQ algorithm. So in terms of stability. So can we do something to improve our method? So we can try to improve the data set. Since it was known that the simulated spectra do not look perfectly real. I mean, it's impossible to simulate exactly what is seen in reality. However, this greatly affected training since these models overfit to the simulation data. So you might produce simulated spectra which produce spectra which are not existing, or you might miss some types of spectra by not considering them. So this is the disadvantage of hard tuning these simulations. But we can try to make this training better by using a type of generative adversarial network. For someone who doesn't know what GANs are, it's not very complicated. So you have this network, which is called a generator, and its goal is to transform a random input into an image. Now, it doesn't know in the beginning what an image is supposed to look like, so in the beginning it's jumbled up, but that's why you have this discriminator, which is trained to classify amongst the real data set and the fake data set. So the job of this guy is to try to understand where the data is coming from. And this architecture is basically a minimax problem where we're trying to minimize the classification loss of the discriminator, but at the same time we maximize at the same time G is optimized so that it maximizes the loss of D, of the discriminator. So we are always trying to create images which will make the discriminator fare worse in the future. So this is the basic principle behind this adversarial training. In this work, I used a variant of GAN, which was called SimGAN. In the original work, a simulator was creating 2D images of eyes with different gazes. The point was to refine these simulations so that the image looks more realistic. And the discriminator was doing the same job as before, trying to distinguish between an unlabeled real image and a refined image. And we can try to apply the same thing to the simulations and real barbecue spectra. This is basically the same thing as the original work. However, it's transformed to fit this problem. And what we can do is we have this data set in red of real barbecue spectra. We have a data set of simulated spectra, and using the same principle of adversarial training, we can train a refiner which is able to create these realistic simulations, such as the work that was there before. So there was a slight problem that I was not expecting, is that one refiner is not enough because it will produce similar looking artifacts. And this comes because the generator is not incentivized to create differences in the output, as long as it always fools the discriminator. So this is a problem with adversarial training. However, if you try 500 of these things with slightly different initial parameters, you can create a refined data set, which is more varied and which potentially holds all the different types of real spectra, or at least more than we were doing before. So we're trying, the whole point of this slide is to obtain this refined data set here. We can get, so these are 3 examples of these refined data sets. So the input of the refiner was a simulated spectrum with no 50 Hertz noise. Simply you add some Gaussian noise to help with because the generator is transforming noise into these artifacts. So you have to inject the simulated spectrum with some Gaussian noise, and the outputs, these are coming from different SimGANs, look surprisingly real, and these spikes were not injected artificially here, they were injected by the network itself. So we can see that it is doing something right here. And the refined approach, which is the final approach, is that we trained the best model architecture that was attempted in the simpler approach, which was the deep neural network called ML1. And when tested on real data compared to the original algorithm, there was an improvement. When seeing this tune evolution for longer time, you can see that this new model is able to more accurately capture the position of the tune regardless of these harmonic spikes. And in terms of its stability metric, it is now we finally have something which is a bit better than the BQ algorithm, which we would expect that if used in real operation, this model would be able to create accurate tune estimates which are relatively stable compared to the current algorithm. So in conclusion, we can train a neural network to estimate the tune from a barbecue spectrum. The naive approach, we just use the data as is. Simple approach, we try to be a bit smarter by simulating them. However, we can overfit to ourselves. And then the refined approach, we're using the advantages given to us by adversarial training to match our simulations with reality without necessarily understanding how they are different. So this is, and in the end, it produced good results. This work was part of this publication. If you have any questions, I'm happy to answer. Thank you.
Many thanks, Leander, for the very, very impressive work. I think it has been very nice that you have shown us the real process of one of these data analysis projects where you go from what is existing and try to improve it in different ways that can fail and then you try something else until it works. So it's very
Exactly.
nice. And yeah, so if there are questions for Leander. No questions? It's looking more like a conference than a workshop. People are not very active. I have maybe a quick question, Leander. There's somebody who has, Marco, sorry.
Oh, please go.
No, you first, Marco.
No, just what was the problem of trying to subtracting the 50 Hertz harmonic and the harmonics from the
problem is that it's difficult to tune it so that you always capture it without fail. So sometimes these harmonics can change a bit by 1 Hertz or 2 Hertz. However, the frequency window that we must eliminate is really small. Otherwise, we'll remove too many data points from the spectrum. So the problem was that it's really prone to this tuning of these, where you have to intercept these harmonics, which is not ideal if used in an operation. Right? I want people to monitor the validity of your harmonics removal. So you can make these windows larger, but then you have less points in your spectrum.
The outcome of the output of your instrument is a spectrum or a time domain signal.
The barbecue, its outputs, you can choose. You can either use the time series data. You can use the spectrum. You can use the spectrum which is filtered as well. I mean, this everything is available to you. But here I decided to not go to time series data in order to have to estimate the tune in a similar way as it was done before. But yes, you can use the time series data as well.
Okay, thank you.
So I have a very quick question. If there are no other questions, maybe from the audience. No, so very quick. Leander, what you've shown seems that could be generalized to similar problems where you have noise, harmonics noise in your signal. Do you think there's anything that here that we would not be able to generalize to another problem where there's a similar spectrum with harmonics?
I don't understand your question.
Yes, so what you've developed seems to be, could be a general purpose system to analyze signals where there is noise, harmonic noise. So it could be the 50 Hertz in the barbecue, or it could be the power harmonics signal in some other system. Mm-hmm. Am I correct, or is there something here that is very specific to the tune, apart from the training sample? Of course, you will have to use other training samples.
I think this method, to if you have a prediction problem and you have no label data, I would say that this is a method which you can use to use the unlabeled data that you already have to improve your simulations, if they are if they can be transformed in a similar way. Yes. I think the whole point here was that you try to train a good predictor without labeled data. So that was the issue with this work. It can be the tune, but I think it can be applied to any other problem which has similar constraints. I think. Did I answer your question or no?
Yes, yes. So you don't see any limitation specific to the tune. It could be generalized. That's your answer.
What I used, the limitation can be the network architectures of this SimGun. So what I did, I used exactly the same networks architectures used in the original work, but I converted them from 2D to 1D because our input is simply a list. It's not an image. However, this is not a trivial architecture. It contains what are they called? ResNet blocks, for example, where you skip connections so that you can make it deeper. And this and the discriminator network is a 1D convolutional network. So these things have to be taken into consideration when you are training these guns, because I try to use a dense network for the refiner, for example. However, it's the fact that you're not, it's might not be deep enough. I mean, if you make it too deep and it's a dense network, the gradients might not propagate efficiently, and so you have to be careful what you use in terms of these architectures.
Okay, thank you.
Okay, now Marco Calvi is reconnected, so we can try.
Can you hear me?
Yes, now, yes. It seems
Okay,
that we have a virus in Zoom, only affecting people called Marco. So please.
So you could hear something before or nothing?
Presentation?
You could hear something?
Yeah. Perfect. Perfectly.
Not before, I mean, you could hear something they were saying or
yeah, we could
almost
hear
nothing because it was interruptions of the audio.
Okay. Good. So thanks for inviting me. So the workshop is very exciting from my point of view, because I'm learning a lot of new things. And so this is the overview of the talk. So I will just give you a few introductory words about LIPS and the Digital LIPS initiative. I will report back from the last spring workshop. So this was the main topic you asked me, but I will then go further, I mean, on the consequences of that workshop, which is the applications for a European call. And I will just give you briefly an idea of what is going on there, and then I will just give you a few conclusions on that. So LIPS is a consortium of light sources in Europe, so user facility. There are 13 storage rings and 6 FELs. And also we have in our labs compact sources, so plasma accelerator. And we have also partners outside Europe, like Sesame and the Canadian light source. So this is how it's organized. So we have a General Assembly, which is our governing board, which is just a meeting of all our directors. There is a coordination board which have to implement the decision. And on the bottom, we have the working group, which are the hearts of the collaborations, where ideas are coming up and are coordinated through the R&D board. And what I'm telling you today is about some ideas coming up from the working group 2 on sources, basically accelerator physics, which I have the privilege to coordinate. And so we are within a larger initiative, which is Digital LIPS. So since the beginning of the pandemic, there was the idea to use, as all of you have done, more digital methods to operate our facility, to get more resilience, efficient, and performance. So at least one of the points at the beginning was just to get access from the outside. So starting from our working group, there was a proposal to develop towards an integrated platform within LIPS laboratories. So it means an IT platform where we can run, let's say, generally we can say digital twins for the operation of our facility towards, let's say, quasi-autonomous operation. But this path was also supported by other colleagues which wanted to work on design of fully automated beam lines. And before starting doing any concrete actions, we say we should make a survey, and that's the origin of the workshop we organized last spring, which had as topics was digital twinning, machine learning, and virtual diagnostics. So, and now I'm just giving you a brief recap of the presentations that had really a small sample. So we had a presentation from seminal facility reporting about existing and operable, let's say, digital twins. We were loose in this definition because we want to be inclusive. Of course, digital twins are, as Nicola and also Pierre was teaching us at the very beginning, I mean, are elements, so are systems which have automatic data flow from the digital object to the physical object, and from the physical object to the digital object. So many of the one being presented were eventually digital models, or in the best case, digital shadow. But all are trying to get into, let's say, this bidirectional connection, where machine learning is definitely the tool for that. So automatic connection wanted, so I think everybody is trying to go in that directions. So application for design, of course, twins can be used for design, but also for the operation of accelerator and X-ray beams transport. The purpose and implementation are very widely. Aspects of complex simulations, so accuracy versus real-time fast feedback, this was addressed, and the computing challenge was, of course, addressed as well. So here, an example of, I would call it a digital shadow from our colleagues from ESRF. This is a talk from Simone Liuzzo, who was the main person developing this model for the commissioning of the new ESRF EBS, so extremely brilliant source. And this could be used for many purposes, also for detecting faults and to see if there is a discrepancy between what is predicted and what is actually measured in the ring. And this was made using the control system Tango, and it was run with MATLAB, but they explained us that they were moving towards Python in June this year, so in principle it should be implemented. I think if Simone is around, I would like to hear from him afterwards. So here a presentation from DAISY, which is operating the European XFL. So here is what you can see from their control room. And you can see that at the bottom, at the bottom of the control system for the European XFL, they have also a virtual XFL, which is definitely a very interesting candidate to become in the future a digital twin of the facility. The European XFL, from the side of the experiments, there are very interesting work, and here is a presentation from Yung Cheng. For making, in this case, is a digital model, from my understanding, do start-to-end simulation from the source, where you can see the generations of synthetic spiky SAS pulse, to photon propagation, to the interaction with matter, and the generation of the signal, and also important to see the response of the detector and data analysis. So I would say one goal could be to put together the previous one and this one, really to build up a full chain from, let's say, from the photocathode down to the experiments. Here, a presentation from the colleagues from Dresden, Casus, which were making a brute force computation of plasma laser wake field accelerator, which could be also used for training surrogate models. The second session was about machine learning. We had the pleasure to have Gianluca Valentino, which was introducing, was making the CISA talk to, and it was explaining us the different possibilities, giving kind of the landscape of possibilities that there are with this technique. So the presentation were even more than before, reported from machine learning tools in operation and under development. The application range from injector to the detector optimization. Method development are ongoing, and application are increasing constantly. So this is just an example from KIT, from Andrea Santamaria, which was showing us really very interesting activities and very different activities that they are carrying out on real-time controls on micro-bunching instability with reinforcement learning, Bayesian optimization of the injections efficiency, and machine learning towards autonomous accelerator, which I think is the future, at least for user facilities. And of course, machine learning is the way to have a fully implemented, fully functional digital twin, because it's definitely needed to have surrogate models. This was presented by Annika from DAISY. And final one, but Aurel was already giving us some details. So we had the pleasure to have Anuka from Slack, which was presenting the work on virtual diagnostic. So we learned this machine learning based diagnostic, so to improve accelerator or more general beam diagnostic by using scalar or spectral diagnostic. So retrieve beam property non-destructively and with higher resolution. In this case, she was really showing us how spectral diagnostic have a higher degree of predictability with respect to scalar one. So in this case, he was showing the example of we are comparing the results using streaking the beam, so in a destructive way, and comparing before the undulators, and comparing this with the information that you can retrieve from a spectrometer just right before the undulators. And of course, this is quite a time consuming, but if you train models on that could be real time, you can get the shot to shot. And this, as it was said before, I mean, it's very important for users to interpret their results. So this is really in a nutshell. So the conclusion of the workshop is that there were 25 speakers over 2 afternoons. So Pierre was excited. It was very compact and full meeting. You can find the presentations on this link. And let's say executive summary was that there was a lot of activity ongoing and merit more support and enhanced integration. So for that reason, we decided to go for a European call, which promised to finance up to 10 million for the next 4 years. So the submission was done on the 23rd of September, and which was not me, was other people which invented this interesting name, DITAR, which is not a video game. It means a digital twins platform for analytical research infrastructure experiments, which has also a meaning, it looks like in Latin, which means enriching. So it's a good wish for the project. So this is the consortium. So we are just 5 LIPS labs. We have neutrons and also electron microscopy within the consortium. And because the call was asking for co-design, which does not mean just you do something for another community, you need really to integrate in the design phase a user community. This was requested, and we choose material science, and we have 6 material science institute which are together. So at the end we are 13. So I was expecting in the US they would not take this number as a very lucky one. So okay, here is DITAR in a nutshell. So the idea is that our facility are complex. And to prepare, execute, and analyze experiments, it takes a long time. And this could be a barrier for a new user, especially to come and to make experiments in our facility. So the proposal is to build a digital twin platform to make preparation, execution, and analysis of such experiment more effective, leading to higher success rate. And the ambition, of course, is that this could became a standard for digital twinning at European analytical research infrastructure. So, and we could reach out even a larger community. So in a more pictorial way, this is the idea, so that you can use this platform to prepare the experiments just with a digital model, just to see what can be done, and then going faster to submit your peer review proposal. And with the digital shadowing, you can optimize and see if you have the right model for running the experiments. And then in the final execution, so you can really go for a full digital twin to optimize parameters, like in an FEL, because below all this, it was, of course, the problem that FEL's experiments are very complex and takes a very long time to be set it up, both from machine side and from the experiments, that some parameters could be optimized automatically, like the pulse duration, bandwidth, and others. And of course, this could be also used offline for the data analysis. And yeah, so this is just a representation of the Daitari ecosystem, where we would like to integrate, of course, the users in the development of this platform. And the platform should make definitions, interfaces, and data format, have the possibility to implement IA method and machine learning tools, should integrate all say already existing modules for describing the sources, typical beam dynamics model, the beam modules for the transport of X-ray, the instruments, the sample, which we have seen before, for instance, in CMEX, and the detectors. So, and the ambition is that, of course, the users will not do it by themselves from the beginning, but it could set up a twin for specific experiments, that they don't need to run a full model of the full facility if some parameters are not relevant. So I would say somehow the example of virtual diagnostics to me is already, let's say, on a nutshell, is already the idea of a twin. So to really control some key parameter during the experiments. And of course, this platform, we would like to have it, let's say, which is independent from the actual hardware or control system. So you can see here in this representation, which actually is an example of the European XFEL, there are already two different control systems in the same facility, one for the machine, as we said, and one for the experiment. So it would be great to have something which is somehow could be shared easily among different facilities within LIPS. So this is just an example of modules which we have identified, and many of the authors are already within LIPS. And we have identified for the call 4 scientific problems to be addressed within this 4 years activity. So the assembling of nature's nanoscale components, next generation of solar cells, damage initiation in structural material, and the fourth, which is the one from where we started, is virtual diagnostics to really control a key parameter during the experiments. So conclusion is machine learning will be the key for the success of Daitari. If positively received from the European Commission and adequately financed, Daitari can foster the development and integration of machine learning method for light sources and beyond. So you are all welcome to contact me if you want to have more information, and we are looking forward to reaching out a larger community. Of course, I have to acknowledge many people. So you see below, I mean, all members of the consortium, all colleagues from the working group from LIPS, and especially thanks goes to Thomas Chencher, which actually I forgot to say that the coordination of Daitari is from the European XFEL, and Thomas did a great job in a very short time to put all this together. So thank you very much. Okay, this was a very different talk with respect to the previous one, not very technical. This was really to let you know what is going on within LIPS in this field.
Thank you very much, Marco, for this very comprehensive report on the workshop, and also information regarding this proposal. I hope you will succeed in getting some funds from the European Commission. Are there questions for Marco?
So my talk was very simple, so I think everybody understood it.
So I have a question, if there are no other questions. what is the possibility of having this approved by the European Commission, and what's the timeline of the proposal of the project?
Yep. So we have been trying to, to get some information from Brussels to see if this proposal was compatible with the call and so on. So we didn't receive any showstopper, neither, let's say, very warm welcome. I think they were just keeping, the mouths shut. Yeah, so we are maybe not at the highest ranking, like could be the European Space Agency, which I think they want to go for digital twin of Earth and so on. So it's already 2 years they're working on that. They have a specific goal that everybody understands. So in our case, really a tool for, let's say, really make, so as it was presented at the beginning of this workshop, I mean, so we need to save time in the setting up of our experiments, so we can really save a lot of money. And so I hope that people will be sensitive to these arguments, and that we are able to attract more people, a new community, new scientific community, which should come to our facility to use them, especially FELs. So the timeline is we will have I hope that we will get an idea of where we are ranked, maybe already before the end of the year. The final answer should be in spring, so 6 months from now. And definitely, if we will be successful, you will hear from us.
Thank you. We have a question for Raimund.
Yep.
Yeah, thank you for the nice presentation. But so if it would work out, how would that got started? So if we look to the overall budget and see the number of institutes involved, and then the 4 years, then it doesn't put out too much money. So one question would be, how would that in the individual institutes be kind of started? So
yeah, so the money is not, so I don't know if I can show you, I mean, the details, but the money are not, let's say, uniformly distributed over all partners. This is clear. So, let's say the material science institutes, they will receive, let's say, a part to contribute, to co-design. So I think there will be, at least from, I can tell you, I mean, concerning PSI, so which, I mean, we are in this case not eligible. I mean, so we are an associate partner. So we will be financed if the call is well received. We will be financed by Switzerland. So yeah, we should receive something like 1.5 million, which to our view, it should be, for what we are planning to do, it should be enough to foster at least where we would like to work mainly, which is virtual diagnostics, with about maybe 6 postdocs working for 4 years at PSI on that to deliver. So I agree. I mean, the money is not huge, but yeah, as I said, I mean, it's not uniformly distributed.
Okay, thank you again, Marco. So now we have to proceed. So
thank you.
Thank you. So the next speaker is Raimund Kammering. He's going to give us a brief overview on the ongoing activity about machine learning at DAISY. Raimund has been working for 20 years at DAISY within the controls department. Since early years, he was involved in the operation on the automation, starting at the Flash facility to later jump over to the European XFL controls and operation team. He is part of the virtual AI ML related group with the DAISY machine division, responsible for application and operation for high-level controls, but also any machine learning activities at the European XFL machine. So, Raimund. Please.
Thank you. Yeah, thank you for the introduction, and thank you for having us here. So this is a very short talk, so I just have 10 minutes because we split that up between me and Antonin, who will give a real example later on. So to start with, on the last ICALEPCS 2019, DAISY hasn't presented anything on ML or AI or whatever we call that. But I think since then, quite much has happened. And I will give you a brief overview about some activities. Some has been already touched here in the prior talks. So I will have a look to the bundling internal forces where we have the set up in kind of a virtual group, I would call it, intelligent process control, we called it, to not have the ML name in there. I'll try to show you something where we are reaching out to the community, and their Helmholtz community is pretty active in this sector. So we'll have a look to Helmholtz AI. A bit bigger construct here in this sense for DAISY especially is the so-called HIREX collaboration, where we'll have a look to. And I will close with shedding some light on the CDCS and thereby kind of introduce the talk by Antonin. So a bit of recap, DAISY is a quite big institute, I would say, and then here are various facilities named as the radars, but there are even more around which are also complex these days, which are the plasma accelerator or plasma wake field accelerator sources, which are that small that they, I think, don't even shine up here on this slide. So yeah, there are many different machines and different challenges on our campus here, I would say. We heard already nicely this morning that while storage rings are more or less equilibrium machines and thereby in some direction more easy to handle, while FELs are highly non-equilibrium machines, and reproducibility and optimization and all this is a big topic on these machines. And I think we already heard that today, that machine time at European XFL is awful expensive, and preparation is taking a lot of time. So we need some help here, definitely. And I already mentioned plasma accelerators are coming up here, very popular these days. This is highly nonlinear, and I think it's clear that one needs here systems of highly sophisticated computing architecture. So the idea to bundle the forces within the campus, where a lot of activities and smaller groups were already taking place. I wouldn't directly call every one of that machine learning related or that like. We had the idea to pull together all the knowledge from the different domains and set up a kind of virtual group and to have an exchange gremium on that. So I think Slack is even having more formal construction of that. We don't have a real machine learning division in this sense, but as said, we set up this intelligent process control group to kind of pull the people together, exchange knowledge, and also try to port knowledge from the one domain to the other. This has been founded, as said, I think it was maybe already in 2019, but nonetheless, we launched a seminar series, which I think had quite a lot of interesting talks in there. We tend to invite people from outside here. So if you can see, there were a lot of speakers from all over the world. And so I think this is a pretty fruitful and nice gremium to do some exchange on that. There's a word cloud showing here, also one buzzword, Ocelot, which is very popular here and kind of originates from DAISY and is also widely used. So also here, collaboration and exchange of software, of algorithms, of ideas is, I think, a very important thing. Furthermore, is this group kind of coordinating or trying to keep track of various programs which are ongoing? Here, 3 are shown. The Amalea, we have already heard some related talks today where we are also part of this Amalea construction, is already ended in principle. As said, HIREX, I will come to in a minute, and also for the CDCS. So Helmholtz AI, I mentioned, as said, the Helmholtz community is really pushing on AI and machine learning in a very wide range, and Helmholtz is not only active in the radar domain, but in the very different domains. But they set up a so-called artificial intelligence cooperation unit, where we applied for one project already in 2019, which was the termed autonomous as a radar. Also, this term I think we heard quite a lot of times today, and I think that's definitely a hot topic. This is for sure not done. I would say that's was kind of a starter project for getting also into the same old AI structure. That was a collaboration with KIT, or is done in collaboration with KIT. So I think that's a nice partner to work with, KIT, but also Helmholtz AI here in this sense. As said, bit bigger project is the so-called HIREX project, which is again within the Helmholtz construct, the so-called international laboratory. This is a collaboration of 3 partners here, as you can see: DAISY, European XFEL, and SLAC. We had a virtual kickoff. So unfortunately, the whole lab, as we call it, is running in the since the Corona times. So unfortunately, we couldn't meet in person, but this, you can hardly see here, is incorporating all directors, and I think even from the minister from the DOA was present there. It's one meeting. So that's pretty high ranked, even though I'm also not so sure how much money finally is involved there. We have to see how long this runs and how this runs. This construct has a bit more ambitious goals in this sense. So this term stands for reliability, repetition, and results, thereby not only looking to ML or special facilities, but having 4 work packages in different areas, and there all the 3 institutes are also coming in. So definitely work package 1 is machine learning, but then we have the user side with high throughput data handling, which is useful for synchrotrons as also for FELs. Automatic sample delivery also on the user side, European XFEL here, and advanced X-ray optics also a very important topic for the final photon experiments. Within this work package 1, machine learning, that's subdivided into 3 tests, where we have one for the machine learning for accelerators, for free electron light accelerator, machine learning for accelerator optimization. We have one for the storage rings, and we have finally one for lasers, also being here the injector lasers, but also pump and probe, and you know what, there are many lasers around here at DAISY, and they have also common needs. So we started already quite some work, even though I think the test 1.1 is still in the early days. So they are using reinforcement learning for here it's written as a radar optimization. In the next step, it will also be used for trying to kind of start up the accelerator from scratch. For the storage ring, we were able to hire a full-time software developer within the project, who is now kind of revising our software stack to, again, we heard that just a minute ago by Marco, a digital twin for this facility. So also here, that's in the early days, but we are kind of revising our software infrastructure, and I think we are coming up with quite some nice infrastructure, which might also be usable later on for the other projects. And on the laser side, the final idea is to kind of do automatic tuning and optimization of laser profiles by using nonlinear transformation and these days available actuators, so to say. Here we already had a small software tool implemented, which is flattening the burst the European XFEL is sending out in terms of the charge profile. That's already running routinely now on the machine. So I think that's quite some nice result. And with this, I'm hurrying through this to give Anthony some minutes to really show us one of this project within the IPC and the DAISY context, which is reaching out to universities here. Also, the University of Hamburg, but also some other universities here in the vicinity within this construct here, where Antonin is also partly involved, and they call it cross-disciplinary labs. Also here, the idea of having different domains sitting together and maybe being able to have some synergies on this high complex software architectures and that like. And with this, I'm already done. As said, we split the talk into 2 parts, and I don't want to steal Antonin's time. So feel free to ask questions, but we can also later on turn to that.
Thank you, Raymond. Interesting talk, and nice to see that there are activities also involving collaborations with other laboratories in Europe and not only. So we have one question, time for one question if there is one for Raymond. Okay, otherwise we leave some time for the next talk. Again, thank you, Raymond, from Daisy, as announced by Raymond. This is a technical talk regarding failure detection on RF cavities. The speaker is Antonin Sulk. Antonin obtained his PhD degree in computer vision at the University of Konstanz, Germany. In the past, he largely focused on machine learning applied to vision problems, and currently trying to find the overlapping regions where machine learning can help to prevent failures on particle accelerator like XFEL. Please, Antonin. I can't hear you. I can't hear you. Very low level. Better now.
Okay. Okay. Thank you very much for pointing this out. Okay. So yeah. Thank you very much again. So I'm here to present you one of the application of machine learning for failure detection on the radio frequency cavities within DAISY. I'm just going to show you some preliminary results and show you a nice application where the recurrent neural networks can help on such huge and challenging problems. So as Raymond mentioned already, I'm here for DAISY, but I'm also employed by CDC also. I'm part of the CDCS, which is a multidisciplinary lab where people from different subgroups come together and try to help each other with solving their problems in multidisciplinary way. So as you probably know, I'm going to deal with radio frequency cavities, which are, in case of European XFEL, must be extremely efficient. So they are also undergoing a lot of stress, and they are used to their maximum power, or like the goal is to use at the maximum power. But the problem is that they need to they must be superconducting, or like the superconductivity must be preserved. They must be sometimes they suffer from different kinds of failures, where the most important one, or probably the most significant one, is a quench, where the cavity loses its superconductivity properties and needs to be cooled down. So for me, as non-physicist, but for someone whose background is machine learning, I care about the signals. So I have three different types of signals. I have a forward and reflected signals, which come to the input of the RF cavity, and I have a probe amplitude or probe signal, which is output the RF cavity, but I take all three signals together and try to analyze them. So what we did is that we took those three signals, which are measured with respect to the amplitude and also to the phase of the signal, and stacked them. So each one signal is basically 1,820 measures over time, where we have per, let's say, like this is just one signal or one of these signals, and we usually record 3 minutes. So we have in total, we have 6 times 1,820 signals, which is roughly 11,000 signal or 11,000 values. And over the period of 3 minutes, we often have 220 values or 20 signals. And we take this 11,000 dimensional vector and feed it into LSTM network, which consists of 128 nodes. We experiment with different architectures, but the architecture where two stacked LSTM layers turn out to be the best. And the output is simply or likelihood that for given signals or for a given sequence of signals, the cavity is going to fail. So here are some examples of properly functioning cavity. So the red signal is a probe amplitude, blue is forward amplitude, and the green is reflected amplitude. And this is how the cavity signal should look like. So the likelihood or probability of the cavity failing is really low, as we can see on the output of the network. The same for the second slightly different signal, where there is just different inputs, and this input was not used during the training, and we can see that the probability of failing is really low. On the other hand, we have cases where the cavity is failing. So for instance, here on the first signal in the left figure, the green the green signal, which corresponds to the reflected signal on the decay part, is not it's not correctly aligned, and therefore the probability, even before the signal actually got misaligned, the probability is below 0.5, which signs that the cavity is on to fail or is failing. And the last example, or the last signal is clear or is classical quench, where the probe amplitude doesn't align well as we expect, and as we can see, the probability of failing is really high. So those steps are just simple steps in order to predict predict the situation before the quench happened, but we definitely are planning to extend it. We have some ideas by using one-class classification. Also, for better interpretability of the latent code, we would like to use the variational autoencoders. And also, there are, as you saw today, the generative adversarial networks turn out to be quite powerful. So we would also like to try the GANs for training. Over the experiments, apart from already mentioned, the key is normalization and accurate labeling, because what we have is that we have labels for the training data, but the training data are not always perfectly and always absolutely perfectly and correctly labeled, which we are going to improve for the future. And we also have different classes of features. So we have a quench, as I showed you, and we also have a failure where there is a jump in decay on the reflected signal. So yeah, that's all from my side.
Thank you, Anthony. Interesting. I have one question, but before my question, I would like to ask the audience if there are any from them. Okay, so I asked my question. So what is the final purpose of this analysis? Also, preventive maintenance, for example, or prediction of failures in order to react immediately for putting the plant into safe state or something like that.
I think that's all you mentioned is the goal. The point is that right now I have all the faulty data and I don't know what is the root cause of these failures. So in order to prevent any kind of failure, I probably need to know what kind of failure happened or what kind of input signal, or if I have the input signal, I need to know what kind of failure is it. If it's like let's say long-term failure, or if it's like long-term problem that device is broken, or if it's just a quench, which is temporary problem, or to my understanding of the physics behind it, the quench should represent just a problem which is immediate problem with loss of temperature. So to answer your question,
yes, but can we use this analysis offline for example, for predicting some aging of the device, of the cavity and so on?
Yes, because the training data are fixed. So I have a data over last 2 years, or from 2010, from 2020 and 2021, from 1.5 years roughly, or roughly 1 year, and this is probably going to be fixed. So if some of the devices are getting broken, then probably it should be reflected, or if the behavior of signal or behavior of cavity is deviating from the standard behavior, then the likelihood of failing or the output of the network should definitely reflect this.
Okay, thank you. Are there other questions?
Maybe a small comment from my side, Anthony. I know there's a group at CERN working also in similar problems to detect breakdowns of RF cavities. So are you aware of their work? Are you in contact with them already?
With whom? Sorry.
There's a group inside CERN.
I don't know. No, I haven't. Maybe that's a good to know.
So maybe it will be good. Offline, we can try to put you in contact.
Okay, thank you very much. That would be great.
Okay, thank you to all the speakers. This session is closed now. Now, according to the workshop style and goals, we have a final session called Submitted Topics and for Problems and Discussion. Where anybody can present an issue, a case, and ask experts and the audience suggestions, hints, etc. We should have one contribution by Heinz Junkes. Heinz, are you there? Hello?
Yeah. Oh, sorry. Shit. Sorry for that. We have some issues with the network and I have to move out to another room and it's not better there, but I have to wear the mask for the official things. Now I put it. No problem. Okay, I just have one short question about the stuff, the machine learning. And I'm actually in a project called FairMat. This is a German project, and they also want to deal with machine learning. And we are still a very small part of this project. That means we are dealing with the experimental control system. That means we will set up a control system to obtain data. And in this domain, most of them are physicists and chemists, and they all talk about machine learning because it's hype now. I'm not an expert in machine learning, therefore I'm watching the talks today. But they all want to do machine learning. There are some theoretician physicists, and they deal with data, with generated data. They have no problems with machine learning. But the experimentalists, the physicists and the chemists, they all want to do machine learning, but they do not understand, or from my point of view, it's important, the quality of the data we obtain is important. The quality of the data from the experiment we obtain. And in your community, or I'm also in this free electron laser community, we all deal with perfect control system like EPICS and Tango mentioned today. But the standard physicists and the chemists, they run experiments with homemade programs, with proprietary software from companies, with LabVIEW stuff or whatever. And I'm thinking for the machine learning, what are the requirements for the data, for the obtained data? The quality of the data, resolutions, and all these things. And I never saw any recommendation what the control system should provide that machine learning will work. This is my question.
Okay, thank you. So you are all invited to answer. Please, Pierre.
We cannot hear you, Pierre. No. Are you unmuted? No. Now,
okay. To try to exit and enter again. We are waiting for you.
But I think it was working, no? We just had a word from you, Pierre. No, it doesn't work.
We have a message on the chat by him. In the meanwhile, if also Aurélie and Verena are there, they are also welcome if they can say something.
I think Verena had to leave. Aurélie is connected. And maybe you can say that Pierre is trying to answer on the chat. So he's saying most learning is affected by data quality.
Yeah.
And then that you require for data cleaning, you require a lot of information, metadata like machine status and so on. And then you need to have like a database with all this information.
So Pierre, apart from that, what can you suggest to Heinz in order to start? Which tools or documentation books can use to start with? Or can you recommend contacting some people can do the same, can face the same problems as him?
Pierre already knows that I'm running the Blue Sky and the EPICS part, but most of these other people in this consortium, they never heard about this. They run smaller experiments, and therefore I would like to know if there's a real general recommendation about metadata, which is absolutely needed, in which quality and with timestamps and what resolution and all these things. I never heard of on the talks that someone specifies the quality of the data exactly. But
I think, Heinz, this is part of the process. I think you will not get right. I think for me, it's an illusion to get right from the beginning these questions. So you have to start to analyze the data, and then you will find out that there is maybe the data is not taken at the right frequency, or maybe that you need more sensors. So it's a bit of an iterative process. It's good to have a good start, to start about it at the beginning, but when you go and analyze, you will find that there are issues with the data, for sure. I mean, I don't know anybody who said, okay, I'm going to do now an analysis, and I have all the data there, it's all perfect. Normally you have to go back and say, I will need now more of this, more of that, or whatever. I mean, Raymond wants to contribute. So Raymond, sorry.
No, fine. That's exactly also one point I would say one needs to make. So it's kind of iterative. That's what we are also experiencing. So we are, maybe I can term it like that, a little bit like late guys in this game, but still now we are trying to match our data pool, data lake, whatsoever, to the tools we see these days. And that is a big challenge. I would say that's even one of the biggest challenge. So getting the data flows, the data structures correct, and having the tagging and the metadata in the right format, in the right flow, that's a big part of the problem. And especially also for that, what Antonin showed, these cavities, for example, produce terabytes within days, within a day easily. So the amount of data, I think these are most probably more the problematic things. Make yourself sure what are the maximum amounts of data and try to adapt your control system to properly handle that in the end. So I think that's a good thing to think about. ML application from the beginning enables you to attach your control system in a way that it's able to handle that and easy to work on the data later on.
Thank you, Raymond. We have a raised hand by Anthony, and then a message also from by Amelia written in the chat. And please, Anthony.
Yeah, I just wanted to mention that as Raymond mentioned, if in case of this RF cavities, for me, the most important part, as I mentioned in the presentation already, is the normalization. And of course, someone has to label the data. And I'm using only a very tiny fraction of the data which are produced by XFEL, but I still have 300 gigabytes of training data. So one has to really carefully think what kind of data you have to use. So very often we are facing different problem than other machine learning experts, where we don't have a problem with lack of data. We have too much data, and we have to be really picky. What kind of data do we want to use?
Maybe we can ask Amelia to read his note. Amelia? Amelia is connected. You don't want to read, to make your comment? Yeah, well, basically, Amelia is telling us some guidelines about how many data samples to take, and also, they should be taking data should be acquired always in a consistent manner. I think this depends on your experiment or your problem. You can do this or not. And also to take care about the sampling rates.
You have again, Anthony?
Yeah. Yeah, this is the problem with the amount of data is always I think the relation is exponential. So with every feature dimension, so if you have 10 dimensions, then you need to have exponentially many input data. So you always have to consider, if you have like really huge problem, to not to overfit to not to have very few data points, because then you have a different problem and it's overfitting. So it's this problem is that this phenomenon is called curse of dimensionality.
Yeah. But this is also assuming you already know how many features you are looking for at the beginning.
Sorry?
This also assumes the number of the number of features you are going to have.
The number of features is a dimension of the problem. So if you, in my case, it's, for instance, in my case with this quench detection, it was roughly 11,000 features. Yeah.
Okay. So I don't know, Heinz, if there has been some help, or is
yeah,
even
sure.
more
Thank
complicated
you.
now.
No, it's okay. It's okay. Thank you. The problem in this domain is this is very special domain. The physicists and the chemists with smaller experiments, mostly they buy systems from companies, set up the systems, and collecting data in a property format or whatever, which is set up by the company. And after they got the data, now the machine learning is in hype. And they want to do machine learning, and they have no chance to optimize the experiment because this is fixed from the company. And this is the problem, that very often they start with not enough data, and then they want to do machine learning with not enough data, and this will not work. And the problem is, if you are the guy on the other side, which is doing the control system and the stuff, you have no, and they will not ask you what you think about this, and they will not set up a system that they can do machine learning. They want to do machine learning after they collected the wrong data or whatever. This is the problem in this domain, and therefore I ask this question: if there is a special knowledge in your domain how to deal with this situation. Also, that was might be a more social problem or whatever. I don't know. Yeah, but thank you for your suggestions, and I really appreciate it. Yeah, it was a wonderful discussion today, and a workshop. Yeah, I learned a lot.
Thank you.
Thank you, Heinz.
So Pierre, you want to say something?
Well, I think everything has been said, and I think we see a similar issue that has been, let's say, 20 years ago with computing systems. These days in science, we're used to open access systems, and I think just data gathering has to get a bit more widespread now that these days you can have epics or Tango on nearly any machine. And I think it's just about distribution, and that people just will demand open access to the data.
There is an old saying about databases. Maybe, I'm not sure this is a strong word in English, sorry, but I will say that many years ago, everybody says in a database, if you put crap in, you get crap out. So it's also something I think you can apply here. If the basic, you have to be able to gather good data from the beginning, or if not, as we said before, iterate back.
Okay. Other contributions for this topic? Are there any other issues or cases you want to put on the table for discussion now? Okay. If not, we can pass to the conclusions, Manuel?
Yes, so still, it's good that still some people to hear the conclusions. Will be short. So yeah, many thanks to everybody for coming today, and especially for all the speakers, and even more special for the overview speakers that had to have longer presentations. I think we have seen a very wide range of applications. So I think the application of these techniques is getting real. It's not theoretical. So we're seeing more in practical terms. I'm still missing, I think we are maybe too much biased to the accelerator community. It's a pity thing. I wanted to ask Gianluca, but he left already some time ago, about more the other communities, telescopes or other communities, if they are also, it would be nice to hear from them what they are doing. So if you are in this community, maybe you can contact us before and then afterwards, and we can discuss also. And yes, so I hope it was useful to all of us, and see you maybe in the next workshop, and hopefully also during the conference we can discuss the topic. So I give the word to Marco. Also thanks to Marco for the very nice collaboration we have organized in these workshops. It has been very nice.
Yeah,
so,
first of all, I would thank you, Manuel, for the fruitful collaboration again for this workshop, and all the audience, and especially the speakers who spent a lot of time preparing the presentations, full of good quality. So thank you, and see you next week for the conference.
And thanks to the organizers. Sorry, Yimbing and Pinja.
Of course, always present and reactive. Thank you very much to you. Thank you.
Okay. Bye-bye.